The universe, a vast expanse filled with endless mysteries, captivates our imagination like nothing else. From the early stargazers who mapped the night skies to modern astronomers exploring the cosmos through powerful telescopes, our fascination with space has only grown deeper. Imagine looking up at the night sky and realizing that the light you see from the stars is ancient, traveling for millions, even billions of years before reaching your eyes. Light from the Andromeda Galaxy, the closest spiral galaxy to our own, takes about 2.5 million years to get here. Essentially, when you observe Andromeda, you're looking at the past, a snapshot of a time when humanity had not yet walked the Earth. As we explore deeper into the cosmos, black holes present one of the most enigmatic subjects. These celestial objects, formed from the remnants of massive stars after a supernova, have gravitational pulls so strong that not even light can escape. The closest known black hole, V616 Monocerotis, lies about 3,000 light-years away from us. But despite their formidable nature, black holes are actually quite common throughout the universe, with potentially millions scattered across our own galaxy alone. Yet, they remain mostly invisible, detectable only through their effects on nearby stars and gas. Another mind-bending concept is time dilation, a result of Einstein's theory of relativity. As an object approaches the speed of light, time for it slows down relative to those who remain stationary. This means that if you could travel at near light speeds through space, you'd age more slowly compared to people back on Earth. Imagine a space traveler leaving Earth, journeying close to the speed of light, and returning to find that decades have passed for those on the planet, while they've only aged a few years. The twin paradox demonstrates this beautifully, suggesting that time itself bends and stretches depending on how fast you move. The largest structure ever found in the universe is a group of quasars known as the Large Quasar Group, LQG. This massive structure spans about 4 billion light-years across, challenging our understanding of how the universe is supposed to be organized. According to current theories of cosmology, no structure should be larger than 1.2 billion light-years, making this discovery a major puzzle for astronomers. The LQG's existence hints at the possibility that our universe is more chaotic and complex than previously thought. Closer to home, our solar system holds its own share of mysteries. Take Saturn's moon, Titan, which is larger than the planet Mercury and boasts lakes, rivers, and seas, not of water, but of liquid methane and ethane. Titan's thick, nitrogen-rich atmosphere and weather patterns that eerily resemble Earth's have made it a prime candidate for future space exploration. Beneath its icy crust, scientists speculate there might be a hidden ocean of water, potentially capable of supporting life. NASA's Dragonfly mission, set to launch in the 2030s, aims to delve into Titan's atmosphere and unlock its secrets. Our very own Milky Way galaxy is a spiral-shaped marvel containing over 100 billion stars. Yet, despite its size, the center of our galaxy is home to Sagittarius A*, a supermassive black hole with a mass equivalent to 4 million suns. This black hole, surrounded by swirling stars and gas, acts like a cosmic anchor, pulling everything around it with an invisible grip. Astronomers have recently observed stars orbiting this black hole at mind-boggling speeds, some moving at up to 8% of the speed of light. The study of Sagittarius A* provides insights into the extreme environments that exist near black holes. Space isn't just full of distant galaxies and black holes. It's also home to rogue planets, planets that wander the galaxy without a star to orbit. These planets, untethered by any solar system, drift through the interstellar void, bathed in the faint glow of faraway stars. Some estimates suggest there could be more rogue planets in our galaxy than stars. If that's true, these lonely wanderers might vastly outnumber traditional planets like Earth. Such a discovery opens up a new avenue of exploration, hinting that life could exist in places we never thought to look. One of the most mysterious phenomena in space is dark matter, a substance that makes up about 85% of the matter in the universe, yet remains invisible to telescopes. Dark matter doesn't emit, absorb, or reflect light, making it detectable only through its gravitational influence on visible matter, like stars and galaxies. Scientists believe that without dark matter, galaxies wouldn't hold together. They'd spin themselves apart. While we've known of its existence since the 1930s, dark matter continues to elude our understanding, sparking ongoing research and debates in the scientific community. In 2017, astronomers detected the first interstellar object passing through our solar system, Oumuamua. Unlike comets and asteroids from our own solar system, Oumuamua's elongated shape and strange trajectory suggested it originated from another star system. Its mysterious speed up as it left our solar system puzzled scientists, leading some to speculate that it might be an alien probe, although no concrete evidence supports this theory. Oumuamua remains a cosmic enigma, a reminder of how much we still don't know about the vast stretches beyond our solar system. Even more astounding is the fact that our universe is expanding, a discovery first made by Edwin Hubble in 1929. He observed that distant galaxies are moving away from us, suggesting that the fabric of space itself is stretching. This expansion is accelerating due to a force known as dark energy, a mysterious force that makes up about 68% of the universe. Dark energy is one of the greatest puzzles in modern physics, as scientists are still unsure of its true nature or why it exists at all. Yet, it is this very force that shapes the future of our universe, determining whether it will continue to expand forever or collapse back into a big crunch. At the edge of what we can observe, there exists a concept known as the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. This faint radiation fills the entire universe, acting as a snapshot of the infant cosmos, just 380,000 years after its birth. The CMB provides a treasure trove of information about the early universe, helping astronomers understand how galaxies formed and why the universe appears the way it does today. By studying this ancient light, scientists are piecing together the story of the universe's beginnings, a story that stretches back over 13.8 billion years. Our closest star, the Sun, also holds incredible secrets. It is a massive ball of hydrogen and helium, burning through millions of tons of fuel every second. Yet, in about 5 billion years, the Sun will exhaust its hydrogen supply and swell into a red giant, engulfing the inner planets, including Earth. After shedding its outer layers, the Sun will become a white dwarf, a dense, cooling remnant roughly the size of Earth. This transformation is a fate shared by many stars, offering a glimpse into the distant future of our solar system. As we continue to explore space, the potential for discovering alien life becomes ever more tantalizing. Recent findings suggest that there may be billions of Earth-like planets in the habitable zones of stars in our galaxy alone. The discovery of extremophiles, organisms that can survive in the harshest conditions on Earth, suggests that life could exist in environments we once thought impossible. From the icy moons of Jupiter and Saturn to the subsurface oceans of exoplanets, the quest for life beyond Earth remains one of the most profound endeavors of humanity. But even the known universe has its limits. Beyond the observable universe lies a region we will never be able to see or reach due to the speed of light and the ongoing expansion of space. It's a reminder that no matter how advanced our technology becomes, some mysteries may remain forever beyond our grasp. Yet, this very unknowability is what drives our curiosity, pushing us to look further, question deeper, and dream beyond the stars. The quest to understand the universe has led us to some truly bizarre phenomena, including the concept of neutron stars. These remnants of massive stars that have gone supernova are incredibly dense. Imagine something with a mass greater than our sun packed into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh about 6 billion tons. Their gravity is so intense that if you were to stand on the surface of a neutron star, you'd be crushed instantly by a force billions of times stronger than Earth's gravity. Neutron stars can also spin at incredible speeds, up to several hundred rotations per second, creating pulsars, lighthouses of the cosmos that emit beams of radiation detectable from Earth. Then there's the phenomenon of magnetars, a rare type of neutron star with a magnetic field that is trillions of times stronger than Earth's. Magnetars can release massive bursts of gamma rays that could fry electronics on nearby planets. In fact, a burst from a magnetar 50,000 light-years away in 2004 was detected on Earth, temporarily impacting our planet's atmosphere. These celestial giants, though incredibly far from us, serve as reminders of the raw power that exists beyond our small corner of the universe. Another fascinating aspect of the cosmos is the process of star formation. Stars are born in vast clouds of gas and dust known as nebulae. One of the most famous is the Orion Nebula, visible even to the naked eye. Within these nurseries, gravity pulls gas and dust together until nuclear fusion ignites, and a new star begins to shine. Yet, star formation is not uniform. Some regions of space are rich in new stars, while others are barren. The Hubble Space Telescope has given us stunning images of these star-forming regions, revealing the chaotic and beautiful nature of the universe's stellar cradles. Moving from stars to planets, some of the strangest worlds discovered so far are exoplanets, planets that orbit stars beyond our solar system. Take the planet HD 189733b, a gas giant with winds that blow at 5,400 miles per hour and temperatures hot enough to melt glass. On this planet, it rains glass sideways, an environment so extreme that it stretches our understanding of what planetary weather can be like. Another exoplanet, Kepler 10b, is a rocky world with a surface temperature of over 2,500 degrees Celsius, so hot that its surface is likely covered in molten lava. These discoveries challenge our notion of what planets can be, suggesting that the universe is home to worlds stranger than any we could have imagined. One of the most iconic objects in the universe is the supernova, the explosive death of a star. When a massive star reaches the end of its life, it can no longer hold back the force of gravity, leading to a catastrophic explosion that outshines entire galaxies for a brief time. The remnants of these explosions, like the Crab Nebula, provide a glimpse into the dramatic processes that shape the cosmos. Supernovae also play a crucial role in spreading heavy elements like iron, gold, and uranium throughout the universe. In a way, the iron in your blood and the gold in your jewelry were forged in the hearts of ancient stars that exploded billions of years ago. In the realm of cosmology, one of the most puzzling questions is the fate of the universe itself. Will it continue to expand forever, gradually cooling as galaxies drift apart into the darkness? Or will gravity eventually win out, pulling everything back together in a big crunch? Or perhaps we live in a multiverse, where our universe is just one of many bubble-like realms floating in an eternal sea of possibilities. Some theories even suggest that new universes could be born from the collapse of stars into black holes, creating a cycle of cosmic birth and rebirth. While these ideas are highly speculative, they highlight the limits of our understanding and the endless potential for new discoveries. In 2020, astronomers made a surprising discovery: a system known as TOI 700 with a potentially habitable planet, TOI 700d, located 100 light-years away. This planet orbits within the star's habitable zone, where temperatures might allow liquid water to exist. While it's too far to reach with current technology, missions like the James Webb Space Telescope are working to study its atmosphere for signs of life. The prospect of finding a world similar to Earth raises profound questions about our place in the universe and whether life, in some form, could be common among the stars. Our solar system itself holds many unsolved mysteries. For example, astronomers have long speculated about the existence of a ninth planet, often referred to as Planet 9. This hypothetical planet, much larger than Earth, is believed to be lurking far beyond Pluto in the distant Kuiper Belt. The unusual orbits of some icy bodies in this region suggest that a massive object might be exerting its gravitational influence. While direct evidence of Planet 9 remains elusive, the hunt for this hidden giant continues, with the potential to reshape our understanding of the solar system. Even the empty spaces between galaxies are not truly empty. These regions are filled with a thin plasma of hot gas, known as the intergalactic medium, which accounts for a significant portion of the universe's ordinary matter. This gas is so diffuse that it's almost a perfect vacuum, but it plays a critical role in the formation of galaxies. As galaxies move through this medium, they can lose gas and slow down, altering their growth and evolution. The study of the intergalactic medium helps scientists understand how galaxies like the Milky Way came to be, providing a deeper look into the life cycle of cosmic structures. Another captivating phenomenon is gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects like colliding black holes or neutron stars. Predicted by Einstein over a century ago, these waves were first directly detected in 2015 by the LIGO Observatory. Since then, scientists have observed dozens of events, revealing a new way to study the universe. Gravitational waves offer a unique window into cataclysmic events, allowing us to hear the collisions of black holes and neutron stars across billions of light years. This new field of astronomy is transforming our understanding of the most violent and energetic processes in the cosmos. The concept of a cosmic horizon, an edge beyond which we cannot see, adds another layer of mystery to our universe. This horizon exists because the universe has a finite age, and light from beyond a certain distance hasn't had time to reach us. As the universe expands, more of it slips beyond this horizon, becoming forever unreachable. It's as if we are living inside a growing bubble, with the edge of the observable universe marking the limits of our cosmic neighborhood. This realization is both humbling and exhilarating, suggesting that there is far more to the universe than what we can see or study. But amidst all these vast and violent phenomena, the smallest particles also hold the keys to understanding the cosmos. Neutrinos, for example, are nearly massless particles that pass through matter almost undetected. Trillions of them pass through your body every second without you even noticing. Yet, studying these elusive particles can reveal information about the core of the sun, supernovae, and even the early universe itself. Neutrino observatories, like IceCube in Antarctica, are working to capture these ghostly messengers, providing insights into some of the most energetic processes in the universe. And then there is the mystery of the Great Attractor, a gravitational anomaly pulling our Milky Way and thousands of other galaxies towards it at over 600 kilometers per second. Located about 150 million light-years away, it lies in a region of space known as the Zone of Avoidance, obscured by the Milky Way's own dust and stars. Despite this, its gravitational influence is undeniable, and astronomers are working to understand what lies at its heart. Is it a massive cluster of galaxies or something stranger? The Great Attractor reminds us that even within our relatively familiar cosmic neighborhood, there are still secrets waiting to be uncovered. These mysteries and wonders, from the smallest particles to the grandest cosmic structures, paint a picture of a universe that is as beautiful as it is mysterious. It's a place where stars are born and die, where time and space bend, and where the quest for understanding drives us to explore farther than ever before. Yet, despite all our knowledge, the universe retains its secrets, urging us to continue our journey of discovery. The vastness of space, with its endless possibilities, ensures that the search for answers will never truly end. As we continue to unravel the mysteries of the cosmos, we stumble upon phenomena that challenge our understanding of reality itself. Take, for instance, the concept of cosmic strings, hypothetical one-dimensional defects in space-time that may have formed in the early universe, shortly after the Big Bang. These incredibly thin structures, thinner than a proton but immensely dense, could stretch across millions of light years. Some theories suggest that cosmic strings might create gravitational waves, or even warp space-time enough to act like cosmic magnifying glasses, allowing us to observe faraway parts of the universe. While we have not yet detected them, the possibility of such exotic structures existing adds a new dimension to our understanding of space-time. Then there's the strange world of antimatter, a mirror image of ordinary matter with opposite charges. When matter and antimatter come into contact, they annihilate each other, releasing energy. This concept, central to many science fiction stories, has a very real basis in physics. The mystery deepens when we consider that the universe seems to contain far more matter than antimatter, despite theories suggesting they should have been created in equal amounts during the Big Bang. This asymmetry, known as baryon asymmetry, remains one of the biggest puzzles in cosmology. Experiments like those at CERN's Large Hadron Collider aim to unlock the secrets of antimatter, offering clues to why we live in a universe made of matter. Our understanding of space has also been transformed by the discovery of exomoons, moons that orbit planets outside our solar system. While thousands of exoplanets have been identified, finding exomoons is a much trickier endeavor due to their smaller size. However, recent studies have suggested possible candidates, like a moon orbiting the exoplanet Kepler 1625b, about 8,000 light-years from Earth. If confirmed, it would be the first exomoon ever detected. Such discoveries could provide new insights into planetary formation and the potential for life in distant star systems, expanding the scope of our cosmic neighborhood. Another fascinating area of study is the potential for life on planets that orbit red dwarf stars, which are smaller and cooler than our Sun. Red dwarfs are the most common type of star in the Milky Way, meaning that there could be countless planets in their habitable zones where liquid water might exist. However, these stars often emit powerful flares, which could strip the atmospheres from their planets, making it difficult for life as we know it to survive. Yet, recent discoveries such as the Earth-sized planets orbiting the red dwarf TRAPPIST-1 suggest that some of these worlds might have the right conditions for life. Studying these planets is a major focus of upcoming space missions, as they may provide our best chance to find life beyond our solar system. One of the most curious phenomena observed in recent years is the existence of fast radio bursts, FRBs, intense bursts of radio waves that last only milliseconds but carry as much energy as the Sun emits in a day. First discovered in 2007, these mysterious signals come from far beyond our galaxy, and their origins remain largely unknown. Some theories suggest they could be caused by the collapse of neutron stars, while others propose that they might be signals from advanced alien civilizations, though there is no direct evidence to support this. The study of FRBs is still in its infancy, but as more of these bursts are detected, scientists hope to decode their source and understand what drives these powerful cosmic flashes. On the scale of cosmic time, our universe is still relatively young, and its fate remains a topic of intense study. One possibility is the Big Freeze, where the universe continues expanding until all stars burn out, leaving a dark, cold cosmos where even atoms decay. Another theory, known as the Big Rip, suggests that the acceleration of the universe's expansion will eventually tear apart galaxies, stars, and even atoms, leaving nothing but isolated particles. Yet, there's also the idea of cosmic rebirth, where the universe might collapse in a big crunch and then be reborn in a new Big Bang, creating a cyclical pattern of destruction and creation. These theories push the boundaries of human understanding, challenging us to think beyond our immediate experiences and consider the ultimate destiny of all that exists. Our understanding of gravity itself is undergoing a transformation with the study of quantum gravity, which aims to reconcile general relativity and quantum mechanics. These two pillars of modern physics describe the large-scale structure of the universe and the behavior of particles on the smallest scales, respectively. Yet, they are fundamentally incompatible, leading to paradoxes when applied to phenomena like black holes or the Big Bang. Theories like string theory and loop quantum gravity attempt to bridge this gap, proposing that space-time might have a discrete, quantized structure. If proven, such theories could revolutionize our understanding of the cosmos, offering a glimpse into the nature of reality at its most fundamental level. In the heart of many galaxies, including our own, lie quasars, extremely luminous objects powered by supermassive black holes. These cosmic beacons can outshine their host galaxies, emitting radiation across the electromagnetic spectrum. Quasars are often found at the centers of distant, young galaxies, providing a window into the early universe. The immense power of quasars comes from the accretion of matter around black holes, where gas and dust are heated to millions of degrees as they spiral inward. Observations of quasars have helped scientists understand the growth of black holes and the evolution of galaxies, revealing a dynamic universe in its formative stages. Another mind-boggling concept is the idea of white holes, theoretical opposites of black holes. While black holes draw in everything that comes too close, a white hole would be a region of space-time from which nothing can enter, only exit. Some theories suggest that white holes could be connected to black holes via wormholes, forming a tunnel through space-time. Though no white holes have been observed, their existence remains a tantalizing possibility in the strange landscape of theoretical physics, offering a potential pathway for understanding the deeper fabric of reality. In recent years, scientists have also discovered the existence of rogue black holes. Black holes that have been kicked out of their galaxies due to gravitational interactions with other supermassive black holes. These cosmic wanderers drift through the void between galaxies, invisible except through their gravitational influence on nearby stars and gas clouds. The discovery of such objects challenges our understanding of how galaxies and black holes interact, suggesting a more chaotic and dynamic universe than previously thought. Dark energy, the mysterious force driving the accelerated expansion of the universe, continues to confound scientists. Observations of distant supernovae in the late 1990s revealed that not only is the universe expanding, but the rate of expansion is increasing over time. This discovery led to the idea of dark energy, but its true nature remains elusive. Some theories suggest it could be a property of space itself, while others propose that it might be a new form of energy field permeating the cosmos. Understanding dark energy is one of the greatest challenges in modern physics, as it holds the key to the ultimate fate of the universe. Yet not all mysteries of space are about distant stars and galaxies. One of the most intriguing objects within our solar system is the dwarf planet Pluto, which has defied expectations since the New Horizons probe flew by in 2015. Images revealed a surprisingly young and active surface, with ice mountains, smooth plains, and signs of possible cryovolcanism, volcanic activity involving water and other frozen substances instead of molten rock. Pluto's complex geology suggests that even distant and small worlds can harbor surprises, challenging our understanding of planetary evolution. Another enigma is the Oort cloud, a hypothetical cloud of icy objects surrounding our solar system at a distance of up to 100,000 astronomical units. Thought to be the source of long-period comets, the Oort cloud marks the outermost boundary of our solar system's influence. Yet, it remains entirely theoretical, as no direct observations have been made. Understanding the Oort cloud could shed light on the formation of the solar system and the early conditions that shaped our cosmic neighborhood. In exploring the universe, we have also encountered the limits of our knowledge about time itself. The concept of time travel, long a staple of science fiction, has roots in real physics, particularly through the idea of time dilation and wormholes. Wormholes, if they exist, could potentially connect different points in space and time, allowing for a form of time travel. However, creating or stabilizing such a structure would require exotic matter with negative energy, something that remains purely theoretical. While time travel might be far from our reach, studying these possibilities helps scientists explore the deeper questions about the nature of time and space. These cosmic puzzles, ranging from the potential existence of cosmic strings to the mysteries of dark energy, remind us of the vast unknowns that lie beyond our current understanding. As we peer deeper into the universe with ever more advanced telescopes and probes, we come closer to answering age-old questions about our place in the cosmos. Yet, each discovery seems to open up new avenues of inquiry, proving that the universe is not just vast in its size, but also in its capacity to surprise and challenge us. In this dance of discovery, we are constantly reminded that, for all our progress, we are still standing on the shores of a boundless cosmic ocean. The mysteries of space continue to unfold as we turn our gaze towards the strange behavior of light itself when influenced by massive objects. One such phenomenon is gravitational lensing, where the gravity of a massive object, like a galaxy or cluster of galaxies, bends the light from objects behind it. This bending of light creates a cosmic magnifying effect, allowing us to see distant galaxies that would otherwise be invisible. It's like nature's telescope, providing astronomers with a way to study the distant universe. Some of the most famous images from the Hubble Space Telescope, like the Einstein Cross, show the dramatic arcs of light caused by this cosmic distortion, giving us a peek into regions billions of light-years away. The bending of space-time isn't just limited to light. Time itself can stretch or shrink around massive objects due to gravity, a concept known as gravitational time dilation. In areas of extreme gravity, like near a black hole, time moves significantly slower compared to regions with weaker gravity. This means that if you could hover near a black hole without being sucked in, time would pass much more slowly for you compared to someone far away. In theory, this could allow for a kind of time travel into the future, though the perilous nature of black holes makes this more of a thought experiment than a practical journey. Nonetheless, this idea highlights how our everyday understanding of time is just one perspective in a universe with far more complex rules. The search for extraterrestrial life has also led us to consider some of the strangest possibilities, including the hypothesis of technosignatures. Unlike biosignatures, which look for signs of life such as oxygen or water, technosignatures are signals or artifacts that might indicate advanced technology, like radio waves from an alien civilization or the heat signatures of massive engineering projects, such as Dyson spheres. A Dyson sphere is a theoretical structure that could encircle a star to capture its energy output, potentially making a civilization almost entirely self-sustaining. While no evidence of such structures has been found, the mere possibility expands our imagination of what life could be like beyond Earth. In the 1960s, the discovery of pulsars, a type of rapidly spinning neutron star, was initially considered a possible sign of extraterrestrial intelligence. These stars emit beams of radiation that sweep across space like a lighthouse, creating regular pulses detectable from Earth. When the first signals from pulsars were detected, their regularity seemed too precise to be natural, leading some astronomers to nickname them LGM or Little Green Men. It was soon realized that these signals were natural, but the moment marked a pivotal point in the search for life beyond our planet. Today, the study of pulsars has become a crucial tool in understanding extreme physics, from neutron star composition to testing the limits of general relativity. As we ponder the potential for life in the cosmos, we also consider the conditions under which life might arise. Recent discoveries have revealed the presence of organic molecules in places previously considered inhospitable, such as the icy moons of Jupiter and Saturn. Europa, one of Jupiter's moons, has a subsurface ocean beneath its ice crust that contains more than twice the amount of water found on Earth. This ocean, heated by tidal forces from Jupiter's gravity, could potentially harbor microbial life. Similarly, Saturn's moon Enceladus has geysers that shoot water vapor and organic compounds into space, suggesting a warm ocean beneath its icy shell. These moons are now prime targets for missions like NASA's Europa Clipper, which aims to explore their potential for habitability. Our understanding of planetary systems has been revolutionized by the discovery of hot Jupiters, gas giant planets that orbit extremely close to their stars. Unlike the gas giants in our solar system, which orbit far from the Sun, these planets have orbits that can take just days to complete. Their close proximity to their stars results in surface temperatures hot enough to vaporize rock, creating atmospheres that can be stripped away by stellar winds. The existence of hot Jupiters was a surprise to astronomers, as it challenged existing models of how planetary systems form. This has led to new theories about planetary migration, suggesting that gas giants may form far from their stars and then slowly spiral inward, drastically altering the architecture of their solar systems. Speaking of exotic worlds, consider the newly discovered super-Earths, which are planets larger than Earth but smaller than Neptune. These planets are among the most common types detected in the galaxy, yet we have no direct equivalent in our own solar system. Super-Earths could have diverse compositions. Some may be rocky like Earth, while others could have thick atmospheres of hydrogen and helium. The discovery of super-Earths has opened up new possibilities for understanding planet formation and habitability. Some of these planets lie within their star's habitable zone, where conditions could allow for liquid water. Their study could bring us closer to finding a planet that resembles Earth more than any other we've found so far. The nature of space itself is filled with perplexing concepts, such as the vacuum energy that exists in empty space. According to quantum mechanics, even a vacuum is not truly empty, but is filled with virtual particles that constantly pop in and out of existence. This vacuum energy might be linked to the mysterious dark energy that drives the accelerated expansion of the universe. The idea that empty space could have a form of energy challenges our traditional notions of nothingness and suggests that the universe is far stranger than it appears. Understanding vacuum energy could be key to unraveling some of the deepest mysteries of physics, from the nature of dark energy to the birth of the universe itself. One of the most unusual aspects of the cosmos is the phenomenon of cosmic microwave background radiation, CMB, which serves as a relic of the Big Bang. This faint glow of radiation, detected in every direction of the sky, is a snapshot of the universe when it was just 380,000 years old. The CMB provides critical evidence for the Big Bang Theory and has helped scientists determine the age, composition, and development of the universe. Tiny variations in the CMB, known as anisotropies, have revealed subtle clues about the structure of the universe, such as the existence of dark matter and the seeds of galaxies. It's like looking at a baby picture of the cosmos, offering a glimpse into a time when the first structures in the universe were just beginning to take shape. Closer to home, our understanding of the solar system is constantly evolving as new space missions provide fresh insights. For example, NASA's Parker Solar Probe has traveled closer to the Sun than any spacecraft in history, revealing unexpected details about the solar corona, the Sun's outermost atmosphere. The corona is much hotter than the Sun's surface, a paradox that has puzzled scientists for decades. The Parker Probe's data is helping to solve this mystery, offering a better understanding of solar winds and space weather, which can impact satellites and communication systems on Earth. This research not only helps us understand our own star better, but also sheds light on the behavior of stars throughout the galaxy. Our curiosity about what lies beyond our solar system has led to projects like Breakthrough Starshot, which aims to send tiny, light-powered probes to the nearest star system, Alpha Centauri, over 4 light-years away. Using powerful lasers, these miniature spacecraft could reach speeds of up to 20% the speed of light, allowing them to reach Alpha Centauri in just over 20 years. Such missions, if successful, would mark a significant leap in our ability to explore interstellar space, potentially providing our first close-up look at planets around other stars. Projects like this inspire hope that one day, humanity might become an interstellar species, exploring new worlds beyond the confines of our solar system. The future of space exploration also includes the ambitious goal of establishing a human presence on Mars. NASA and private companies like SpaceX are actively developing the technology needed to send humans to the Red Planet, aiming for a possible landing within the next decade. Mars has captivated us for centuries with its potential to harbor life, past or present. Evidence of ancient riverbeds, dried-up lakes, and underground water reserves suggests that Mars once had a wetter, more Earth-like environment. The idea of terraforming Mars, transforming it into a planet where humans could live, remains a distant dream, but the first steps toward making it a reality are already being taken. A manned mission to Mars would not only be a monumental achievement, but could also teach us invaluable lessons about living on other worlds. As we venture further into the cosmos, we must also consider the potential for finding signs of intelligent life through projects like the Search for Extraterrestrial Intelligence, SETI. Using large radio telescopes, scientists scan the skies for signals that might indicate advanced civilizations. Despite decades of searching, no definitive signs have been found, but the discovery of thousands of exoplanets has renewed optimism. Some scientists argue that the universe's sheer size makes it statistically likely that intelligent life exists somewhere out there, even if it's beyond our ability to detect right now. The Fermi paradox: why we haven't found evidence of other civilizations despite the vastness of the universe, remains a profound question, one that drives our search for answers among the stars. Even as we look outwards, the mysteries of space remind us of our own fragility and the unique conditions that make Earth a cradle for life. The discovery of Earth-like planets and the exploration of our own solar system have deepened our appreciation for the delicate balance that allows life to flourish here. Understanding space isn't just about finding other worlds. It's about gaining perspective on our own place in the universe and how precious our existence truly is. For every new answer, the universe presents us with more questions, urging us to keep looking, keep exploring, and keep wondering about what lies beyond. As our understanding of the universe deepens, we encounter even more perplexing phenomena that challenge our grasp of the laws of physics. One such mystery is the idea of quantum entanglement, often described as spooky action at a distance by Albert Einstein. This phenomenon occurs when particles become entangled, meaning the state of one particle instantly affects the state of another, no matter how far apart they are. Experiments have shown that entangled particles can remain connected even when separated by great distances, suggesting that information might travel faster than light. While this doesn't allow for faster-than-light communication, it points to a fundamental strangeness in how reality operates at the smallest scales. Quantum entanglement has even found practical applications, such as in quantum computing and quantum encryption, hinting at the potential for a future where technology harnesses these peculiar properties of nature. While quantum mechanics governs the microscopic, the universe at large scales is guided by the principles of relativity. The interplay between these two domains becomes especially intriguing when studying the interiors of black holes. At their cores lies a region known as the singularity, where gravity becomes infinitely strong and the known laws of physics break down. It is a point where space and time themselves seem to fold in on each other. Despite extensive study, no one knows what actually happens inside a black hole's singularity. Some theories suggest that black holes might contain entire universes, leading to the notion of our universe being inside a black hole itself. Such ideas stretch the boundaries of scientific imagination, offering glimpses into realms where our current understanding falters. Another enigma in the fabric of the cosmos is the concept of parallel universes, or the multiverse. This idea posits that our universe might be just one of countless others, each with its own set of physical laws, constants, and dimensions. The multiverse theory has gained traction through developments in string theory and the study of cosmic inflation, which suggests that rapid expansion after the Big Bang could have spawned other universes. Some interpretations even propose that every decision we make creates a new parallel universe, leading to infinite variations of reality. While direct evidence of the multiverse is lacking, it provides a fascinating framework for considering the vastness of existence, suggesting that reality might be far stranger than we can perceive. Time itself becomes a curious subject when we consider the possibility of wormholes, hypothetical shortcuts through space-time that could connect distant parts of the universe. In theory, a wormhole could allow faster-than-light travel between 2 points, making interstellar travel possible. However, creating or stabilizing a wormhole would require exotic matter with negative energy, something that we have yet to discover. If wormholes do exist, they could offer pathways not only through space but also through time, raising tantalizing possibilities about the nature of the universe. Yet, like so many aspects of the cosmos, wormholes remain a speculative but thrilling concept, fueling our dreams of exploring the far reaches of space. The edge of our knowledge is also tested by the study of cosmic voids, vast, empty regions between galaxies that can span hundreds of millions of light years. These voids, like the Boötes void, are regions where galaxies are sparse or absent altogether, creating large gaps in the otherwise rich tapestry of the universe. The existence of such voids challenges our understanding of how galaxies form and cluster. Some theories suggest that these voids might result from dark energy or the uneven distribution of matter after the Big Bang. Studying cosmic voids helps scientists probe the large-scale structure of the universe, offering clues about the forces that shape the cosmos into its current form. As we contemplate the extremes of space, it's impossible to ignore the potential of harnessing new forms of energy for future space travel. One of the most promising concepts is nuclear fusion. The same process that powers the Sun fusion reactors aim to replicate this process on Earth, producing vast amounts of energy by fusing atomic nuclei together. If we can perfect fusion technology, it could revolutionize space travel, providing a virtually limitless energy source. With fusion propulsion, spacecraft could achieve speeds far greater than what is possible with current chemical rockets, potentially making interstellar journeys feasible. While still in its developmental stages, the dream of fusion-powered spacecraft represents the next great leap in our quest to reach the stars. Beyond the mechanical challenges of space travel, the physical toll of space on the human body remains a significant hurdle. Extended time in zero gravity can cause muscle atrophy, bone density loss, and changes in vision due to fluid shifts in the body. The microgravity environment of the International Space Station, ISS, has provided crucial insights into these effects, helping scientists develop strategies for maintaining astronaut health. Exercise regimens, dietary supplements, and even research into artificial gravity through rotating habitats are being explored to ensure that future explorers can endure long-duration missions, such as those to Mars. Understanding how to adapt to these challenges is essential if we are to become a spacefaring civilization. The search for life beyond Earth takes an exciting turn when we consider the potential of extremophiles, organisms that can survive in extreme conditions on Earth, from deep ocean vents to acidic lakes and frozen tundras. These hardy life forms have expanded our understanding of where life might exist, suggesting that it could survive in environments previously considered inhospitable. This has profound implications for the search for life on other planets, such as Mars, which has frozen water beneath its surface, or Europa, with its subsurface ocean. The discovery of extremophiles has led scientists to adopt a broader view of habitability, raising the possibility that life might thrive in unexpected corners of our own solar system or in the distant reaches of exoplanets orbiting other stars. As we continue to look for life, the idea of panspermia adds another layer of intrigue. This theory suggests that life might have spread throughout the cosmos via meteoroids, comets, or even interstellar dust. According to this idea, life could have originated elsewhere in the universe and been transported to Earth through impacts or cosmic debris. The discovery of amino acids and complex organic molecules on comets and asteroids has given some support to this idea, suggesting that the building blocks of life might be widespread throughout the galaxy. If true, panspermia would imply that life on Earth is part of a broader cosmic tapestry, potentially linking us to life forms that may have arisen under very different conditions. One of the most awe-inspiring revelations of modern astronomy is the realization that the universe is not static but dynamic, filled with phenomena like gamma-ray bursts, extremely energetic explosions that are the brightest events in the universe. Gamma-ray bursts, GRBs, can release more energy in a few seconds than the sun will emit in its entire lifetime. They are thought to result from the collapse of massive stars or the merging of neutron stars. The discovery of GRBs has provided insight into the death throes of massive stars and the creation of black holes, offering a glimpse into some of the most powerful forces in the universe. Observing these bursts allows us to study events billions of light years away, peering into the distant past and the early stages of the universe. As we study the stars, we are reminded that even in the darkest corners of space, light can be found in unexpected forms. One of the most mysterious of these is the cosmic neutrino background, a relic from the earliest moments after the Big Bang. Neutrinos are subatomic particles that pass through matter with almost no interaction, making them incredibly difficult to detect. The IceCube Neutrino Observatory, buried deep in the Antarctic ice, has begun capturing these elusive particles, offering a new way to study the universe. Neutrinos can provide information about distant astrophysical events like supernovae and black hole mergers, revealing a hidden aspect of the cosmos that traditional telescopes cannot see. Among the strange celestial objects that populate the universe are blazars, a type of active galactic nucleus powered by a supermassive black hole that emits intense jets of radiation pointed directly towards Earth. These jets can be so powerful that they outshine entire galaxies, making blazars some of the most luminous objects in the sky. Blazars are a window into the behavior of black holes and the dynamics of high-energy astrophysical processes. By studying them, astronomers gain insights into how black holes influence their surroundings, sculpting the evolution of galaxies and the structure of the universe. Our journey through the cosmos, from the quantum to the galactic, is a testament to the power of human curiosity and the relentless drive to explore the unknown. Each discovery we make, whether it's the faint signal of a distant planet or the fiery outburst of a dying star, adds a new thread to the intricate fabric of our understanding. Yet, even as we reach for the stars, we are constantly reminded of how little we truly know. The universe remains a place of profound mystery, filled with questions that challenge our imagination and our sense of what is possible. It is this sense of wonder, this willingness to confront the unknown, that keeps us looking up at the night sky, dreaming of what lies beyond. As we continue to peel back the layers of the cosmos, one of the most captivating frontiers lies in the study of dark matter, a mysterious substance that makes up about 27% of the universe's total mass and energy. Unlike ordinary matter, dark matter does not interact with light, making it completely invisible to our eyes and telescopes. We only know it exists because of its gravitational effects on galaxies and galaxy clusters. For instance, when astronomers observe the rotation of galaxies, they find that stars in the outer regions move faster than expected. This discrepancy suggests the presence of a hidden mass, dark matter, creating a gravitational pull that holds galaxies together. Without it, these galaxies would fly apart. Yet, despite its crucial role in shaping the universe, dark matter has remained elusive, with experiments like those at CERN and deep underground detectors still searching for direct evidence of its nature. The universe's dark side doesn't stop at dark matter. It also includes dark energy, a force even more mysterious that makes up about 68% of the universe and drives its accelerated expansion. Observations of distant supernovae in the 1990s revealed that the universe is not just expanding, but doing so at an increasing rate. This discovery upended previous models of the cosmos, suggesting that dark energy is pushing galaxies apart faster and faster. The exact nature of dark energy remains unknown, and it might represent a fundamental property of space itself, known as the cosmological constant. Or it could be a new field entirely, similar to the forces that shaped the universe in its earliest moments. Understanding dark energy is one of the greatest challenges in modern astrophysics, as it holds the key to the universe's ultimate fate, whether it will continue expanding forever, slow down, or end in a dramatic event like the Big Rip. The study of distant exoplanets has also introduced a new dimension to our understanding of planetary atmospheres. Using advanced telescopes like the James Webb Space Telescope, JWST, scientists can analyze the light that filters through a planet's atmosphere when it passes in front of its star. This method, known as transit spectroscopy, reveals the chemical composition of the atmosphere, providing clues about the potential for life. For example, detecting oxygen, methane, or water vapor could indicate conditions favorable for life. Recently, JWST has started revealing the atmospheric profiles of rocky exoplanets in the habitable zones of their stars, raising hopes of finding worlds that resemble early Earth. These detailed observations bring us closer to answering the age-old question of whether we are alone in the universe. Closer to home, the recent resurgence in lunar exploration has focused attention on the moon's potential as a base for future space missions. The discovery of water ice at the lunar poles has been a game-changer, suggesting that astronauts could extract water for drinking, convert it into oxygen for breathing, and use hydrogen for rocket fuel. Projects like NASA's Artemis program aim to establish a sustainable human presence on the moon by the end of the decade, laying the groundwork for deeper space exploration, including Mars. A lunar base could serve as a launch pad for missions to the Red Planet, leveraging the moon's lower gravity to reduce the fuel needed for interplanetary travel. The vision of a moon base, once the stuff of science fiction, is gradually becoming a reality, opening up new possibilities for humanity's presence beyond Earth. Mars, the next frontier, continues to intrigue with the tantalizing possibility of past life. Evidence from rovers like Curiosity and Perseverance has shown that Mars once had a climate that could have supported liquid water on its surface, rivers, lakes, and possibly even oceans. Recently, Perseverance has been exploring the Jezero crater, a dried-up lake bed that may have been home to microbial life billions of years ago. It's collecting samples that future missions plan to bring back to Earth, providing an unprecedented opportunity to study Martian geology and, perhaps, search for signs of ancient life. The discovery of even the simplest life forms on Mars would fundamentally alter our understanding of life in the universe, suggesting that the conditions for life might be more common than we thought. While exploring our solar system, we've also begun to unravel the secrets of its smaller, icy bodies, like comets and asteroids. These remnants from the early solar system offer a snapshot of the materials that formed the planets. Missions like Rosetta, which orbited and landed on Comet 67P/Churyumov-Gerasimenko, have revealed surprising details about these icy wanderers, including the presence of organic molecules. Such findings suggest that comets may have played a role in delivering the building blocks of life to Earth, contributing to the emergence of life. Asteroids, like those studied by the OSIRIS-RX mission, are also valuable time capsules, preserving pristine material from the solar system's formation. By studying these objects, We gain insights into the processes that shaped our cosmic neighborhood billions of years ago. As we look further out, the discovery of star nurseries, or stellar nurseries, offers a glimpse into the birth of stars. These vast clouds of gas and dust, like the Eagle Nebula's pillars of creation, are sites where gravity pulls matter together until nuclear fusion ignites in the core of a new star. Observing these nurseries with telescopes like Hubble and the Atacama Large Millimeter/Submillimeter Array, ALMA, has allowed scientists to witness the early stages of star formation, including the creation of protoplanetary disks, rotating disks of gas and dust that will eventually coalesce into planets. These observations reveal that our solar system's formation was not unique, but part of a process that occurs throughout the universe, suggesting that planetary systems could be a common outcome of star formation. The deeper we look into the universe, the more we encounter the limits of our understanding, as is the case with the cosmic horizon. This boundary represents the furthest distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon lies a realm that is forever beyond our observational reach due to the finite speed of light and the universe's ongoing expansion. As space expands, galaxies beyond the cosmic horizon recede faster than the speed of light, effectively disappearing from view. This limit creates a paradox. There may be regions of the universe that we will never see or know, no matter how advanced our technology becomes. It's a humbling reminder of our place in the universe, confined to a small bubble of space-time from which we can observe the cosmos. While exploring the universe's most distant reaches, we have also uncovered the intriguing phenomena of primordial black holes. These hypothetical black holes may have formed not from collapsing stars, but directly from the high-energy conditions of the early universe. Unlike their massive counterparts, primordial black holes could range in size from tiny particles to thousands of times the mass of the Sun. Some theories propose that they could even account for a portion of dark matter. If primordial black holes exist, they could provide a window into the conditions of the universe just moments after the Big Bang, revealing information about the birth of space and time itself. In the study of galaxy evolution, we have learned that galaxies are not static structures but dynamic systems that can collide and merge over time. The Milky Way is on a collision course with the Andromeda Galaxy, our nearest spiral neighbor. In about 4.5 billion years, these two galaxies will merge, creating a new, larger galaxy, sometimes referred to as Milkomeda or Milkdromeda. During this cosmic dance, stars within each galaxy are unlikely to collide due to the vast distances between them, but their gravitational interactions will drastically reshape the galaxies. Such galactic mergers have been observed throughout the universe, providing a glimpse into the long-term evolution of galaxies and the formation of elliptical galaxies. The eventual merger of the Milky Way and Andromeda is a reminder of the universe's dynamic nature, where even seemingly eternal structures are subject to change. Finally, our journey through the universe is increasingly aided by the rise of artificial intelligence and machine learning, which are transforming the way we explore space. AI is now being used to sift through vast amounts of astronomical data, identifying patterns and anomalies that human researchers might miss. It has helped in the discovery of new exoplanets by analyzing the subtle dimming of stars and in mapping the distribution of galaxies across the cosmos. AI even assists in navigating spacecraft, making autonomous decisions in real time, like guiding rovers on Mars or adjusting the course of interplanetary probes. This fusion of human ingenuity and machine learning is accelerating our exploration, enabling us to uncover the universe's secrets at an unprecedented pace. As we continue to push the boundaries of exploration, the vastness of space becomes both a challenge and an invitation, an endless frontier where each discovery leads to new questions, where each observation reveals deeper mysteries. It's a place where the smallest particles can hold clues to the universe's beginning, and the largest structures can shape its future. From the strange dance of galaxies to the hidden realms beyond our cosmic horizon, space remains a realm of boundless potential. It is this vast, star-filled canvas that beckons us to keep looking up, to seek out the unknown, and to imagine what might be out there, waiting to be discovered. The story of the universe is far from finished, and we are just beginning to understand our part in it. As we continue our journey through the cosmos, we find that the mysteries of the universe only deepen, challenging our understanding of reality and our place within it. One of the most perplexing concepts in modern physics is the idea of cosmic inflation, a theory that suggests that a fraction of a second after the Big Bang, the universe underwent a rapid expansion, growing exponentially in size. This inflationary period helps explain the uniformity of the cosmic microwave background radiation and why distant regions of the universe look so similar, despite being separated by vast distances. It also predicts that tiny quantum fluctuations during inflation became the seeds for the formation of galaxies and large-scale structures we see today. Yet, the exact mechanism behind inflation remains one of cosmology's biggest unsolved puzzles, with scientists searching for evidence in the polarization patterns of the cosmic microwave background to better understand what set the universe into motion. Inflation ties into another profound mystery, the concept of the quantum vacuum. In the quantum realm, even empty space is not truly empty. It is a seething froth of particles popping in and out of existence. This constant fluctuation is what gives rise to virtual particles, which can briefly appear and then annihilate each other. The energy from these fluctuations is thought to contribute to the overall density of the universe, and might even have a role in driving the expansion of space through dark energy. It's a mind-bending idea that the emptiness of space is actually full of activity at a microscopic level, influencing the very structure of the cosmos on the largest scales. Understanding the quantum vacuum could unlock answers about the fundamental nature of reality, bridging the gap between quantum mechanics and general relativity. The search for a unified theory that combines the forces of nature continues to be a central quest in theoretical physics. One candidate is string theory, which suggests that all particles are actually tiny, vibrating strings of energy. The different modes of vibration correspond to different particles, from electrons to quarks to the force carriers like photons and gravitons. String theory requires extra dimensions beyond the familiar 3 of space and 1 of time, potentially up to 11 dimensions. While these extra dimensions are hidden from our view, they could be compactified or curled up at scales much smaller than atoms. If proven, string theory could offer a framework for understanding how gravity works at the quantum level, potentially solving the mysteries of black holes and the nature of space-time. But the lack of experimental evidence means it remains a theoretical frontier, waiting for breakthroughs that might bring it into the realm of observable science. As we probe the structure of the universe, we also confront the strange nature of time itself. Time is often considered a constant flow, moving forward in a linear fashion, but theories like general relativity suggest that time is malleable, affected by gravity and velocity. In regions of strong gravity, like near a black hole, time slows down relative to areas of weaker gravity, a phenomenon known as time dilation. This effect has been measured using atomic clocks placed at different altitudes on Earth, where clocks closer to the surface tick slightly slower than those in space. The idea that time is not a fixed, universal quantity, but a relative experience that changes with gravity and speed challenges our everyday perception of reality, suggesting that the universe operates according to principles far stranger than our senses can grasp. The mysteries of time bring us to one of the most haunting questions in cosmology. What came before the Big Bang? While the standard model of cosmology describes the universe's expansion from a hot, dense state, it is silent about what preceded it. Some theories suggest that the universe could be cyclical, going through an eternal cycle of expansion and contraction, a cosmic bounce rather than a singular beginning. Others propose that our universe might have emerged from a quantum fluctuation in a larger multiverse, where countless other universes could exist with different physical laws. These speculative ideas push the boundaries of science, as they often deal with realms beyond our observational reach. Yet, they encourage us to think about the origin of everything in new ways, challenging the notion that time and space, as we know them, are the ultimate limits. As we peer into the depths of the universe, we encounter structures on a scale that defies comprehension. Take, for instance, the Hercules Corona Borealis Great Wall, a massive galactic structure that stretches across 10 billion light-years, making it the largest known object in the universe. This structure is a colossal cluster of galaxies, bound together by gravity. Its existence challenges the cosmological principle, which states that the universe should appear homogeneous and isotropic when viewed on a large enough scale. The presence of such enormous structures suggests that the distribution of matter in the universe might be more clumpy and irregular than we previously thought, prompting scientists to revisit their models of cosmic evolution and the role of dark matter in shaping the universe's large-scale structure. The exploration of the cosmos has also introduced us to the concept of baryogenesis, the process that led to the imbalance between matter and antimatter in the early universe. According to theory, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe filled with radiation, but no matter. Yet, here we are, living in a universe dominated by matter. This asymmetry remains one of the greatest unsolved problems in physics, with theories like leptogenesis offering possible explanations, suggesting that certain processes involving neutrinos in the early universe could have tipped the balance in favor of matter. Understanding why our universe has more matter than antimatter could shed light on fundamental aspects of the cosmos and explain why we exist at all. Our study of the cosmos is not limited to what lies beyond our solar system. It also includes the search for resources that could enable human expansion into space. Asteroid mining is one such idea, with certain asteroids containing abundant amounts of precious metals like platinum and rare earth elements. These resources could be crucial for developing space infrastructure, potentially providing materials for building colonies on the Moon or Mars. Beyond metals, some asteroids contain vast quantities of water, which could be converted into rocket fuel or provide life support for future spacefarers. While the technology to mine asteroids is still in its infancy, companies and space agencies are already exploring the potential for turning these space rocks into stepping stones for human expansion beyond Earth. Such endeavors could transform our solar system into a bustling network of human activity, extending the reach of our civilization far beyond its planetary cradle. As we continue to explore space, the concept of space elevators has emerged as a potential game-changer in accessing orbit. A space elevator would consist of a cable stretching from Earth's surface to a point beyond geostationary orbit, allowing for a more efficient and sustainable way to transport materials and people into space. The key challenge is finding a material strong enough to withstand the immense tension required for such a structure. Carbon nanotubes and graphene have been proposed as potential candidates due to their extraordinary strength, but manufacturing such materials on a large scale remains a significant hurdle. If realized, a space elevator could dramatically reduce the cost of reaching space, opening up new possibilities for exploration and industry beyond Earth. In the realm of interstellar exploration, the idea of using light sails to travel between stars has gained attention. Light sails work by harnessing the momentum of photons, allowing spacecraft to be propelled by the pressure of light from the sun or powerful lasers. The Breakthrough Starshot initiative aims to develop tiny, light-powered probes capable of reaching the Alpha Centauri star system within a few decades. These probes, traveling at up to 20% the speed of light, could send back images and data from our nearest stellar neighbors. Light sails represent one of the few practical concepts for interstellar travel within a human lifetime, offering a glimpse into a future where we might explore other star systems and potentially discover new worlds. Back in our solar system, the icy moons of the gas giants continue to intrigue scientists with their potential for life. Beyond Europa and Enceladus, Jupiter's moon Ganymede and Saturn's moon Titan are also promising targets. Ganymede, the largest moon in the solar system, has a magnetic field and may harbor a salty ocean beneath its thick ice shell. Titan, with its thick nitrogen-rich atmosphere and lakes of liquid methane and ethane, is a world where the chemistry of life could take on forms vastly different from Earth's. The Dragonfly mission, set to explore Titan's surface in the 2030s, aims to study its chemical processes and search for signs of prebiotic chemistry. These missions reflect our ongoing quest to understand the conditions under which life might arise, even in environments far different from our own. The study of exoplanetary systems has also led to the discovery of planets with orbits unlike anything seen in our solar system. Some of these worlds follow highly elliptical orbits, taking them close to their stars for part of their year before swinging far out into the cold reaches of space. Others orbit their stars and resonances, creating complex gravitational dances with neighboring planets. These discoveries have revealed that planetary systems can be wildly diverse, with configurations that challenge our understanding of how planets form and evolve. The sheer variety of exoplanets, from super-Earths to mini-Neptunes, suggests that the galaxy is filled with worlds of all kinds, each with its own story to tell about the forces that shaped it. As we expand our horizons, it becomes clear that the universe is not only vast in scale, but also rich in diversity, complexity, and mystery. Each new discovery, from the behavior of quantum particles to the dynamics of distant galaxies, adds a new thread to the tapestry of our understanding. The journey of exploration, fueled by curiosity and the desire to know what lies beyond, drives us ever forward. It is a quest that has no end, as each revelation brings with it deeper questions and greater wonders. The cosmos, with all its enigmatic beauty, remains an invitation to explore, to discover, and to dream of what might be out there in the darkness, waiting for us to find. As we delve deeper into the cosmos, we find that the universe is filled with structures and phenomena that stretch our imagination to its limits. One such wonder is the existence of supervoids, enormous regions of space where galaxies are sparsely distributed, creating vast expanses of emptiness. The most famous of these is the Eridanus supervoid, which coincides with the cold spot, an area in the cosmic microwave background, CMB, that is significantly cooler than its surroundings. This anomaly has puzzled scientists since its discovery, as standard models of the universe cannot fully explain why such a large, cold region exists. Some theories suggest that the supervoid could be a naturally occurring feature of large-scale cosmic structure, while more speculative ideas propose that it could be evidence of a collision with another universe. Though these ideas remain unproven, the study of supervoids provides a fascinating glimpse into the irregular and often unexpected nature of the cosmos. Our exploration of space has also led us to consider the potential for life in even the most extreme environments. Among the most intriguing of these are the hydrothermal vents on Earth, where life thrives without sunlight, instead relying on the chemical energy produced by reactions between seawater and the minerals of the Earth's crust. These ecosystems are seen as analogs for potential life on icy moons like Europa and Enceladus, where similar conditions might exist beneath their ice-covered oceans. If life could develop in such darkness on Earth, it raises the possibility that simple or even complex organisms could survive in the hidden oceans of these distant moons. Future missions equipped with robotic probes could explore these subsurface oceans directly, using melting probes or autonomous submersibles to search for signs of life. Such a discovery would revolutionize our understanding of life in the universe, suggesting that life might find a way even in the darkest corners of the cosmos. Another fascinating topic is the study of rogue stars, which are stars that have been ejected from their home galaxies and now wander alone through intergalactic space. These stellar outcasts are thought to be the result of gravitational interactions between galaxies, or the aftermath of supernovae that have kicked stars out of their orbits. Despite being separated from the dense environments where most stars reside, rogue stars offer a unique perspective on stellar evolution and the dynamics of galaxies. They remind us that the universe is not a static place, but a constantly shifting sea of matter and energy, where even stars can be set adrift, traveling through the vast emptiness between galaxies. In the search for understanding the cosmos, one concept that has captivated scientists is the idea of Hawking radiation, proposed by physicist Stephen Hawking in 1974. Hawking radiation suggests that black holes can emit radiation due to quantum effects near their event horizons. This phenomenon would mean that black holes are not entirely black, but slowly evaporate over time, losing mass and energy until they eventually disappear. The existence of Hawking radiation challenges the idea that information is lost when it falls into a black hole, leading to the so-called information paradox. This paradox pits quantum mechanics against general relativity, highlighting a fundamental conflict in our understanding of how the universe works. If Hawking radiation is proven, it would provide a vital link between the quantum and gravitational realms, offering clues to the nature of space-time itself. As we explore the universe's extremes, we also encounter the astonishing power of neutron star collisions. When two neutron stars merge, they produce a cataclysmic event known as a kilonova, which emits gravitational waves and produces heavy elements like gold and platinum. In 2017, astronomers detected gravitational waves from a neutron-star merger for the first time, accompanied by light across the electromagnetic spectrum. This event confirmed that these cosmic collisions are a primary source of heavy elements in the universe, transforming our understanding of how matter is distributed throughout the cosmos. The ability to observe such events through both light and gravitational waves has ushered in a new era of multi-messenger astronomy, allowing us to study the universe in ways that were previously unimaginable. On the topic of gravitational waves, the detection of these ripples in space-time has revolutionized astronomy. Gravitational waves are generated by massive objects accelerating through space, such as colliding black holes or neutron stars. When these waves pass through Earth, they cause tiny distortions in the fabric of space-time, which can be detected by observatories like LIGO and Virgo. The ability to measure these waves has provided a new tool for studying some of the most violent events in the universe. Unlike light, gravitational waves can travel through regions of space that are otherwise opaque, offering a new way to probe the early moments of the universe, black hole mergers, and even the interiors of neutron stars. Each detection adds a new piece to the puzzle of how our universe evolves and interacts. Another astonishing phenomenon is the concept of cosmic shear, a subtle warping of light caused by the gravitational pull of large-scale structures like galaxy clusters. As light from distant galaxies travels through space, it is bent and stretched by the gravitational influence of matter in the universe, creating a sheared image when it reaches our telescopes. By mapping cosmic shear, scientists can create detailed maps of the distribution of dark matter, offering insights into the invisible scaffolding that holds galaxies together. These maps allow astronomers to study how dark matter clumps and influences the growth of structures over cosmic time. This research is crucial for understanding the role of dark matter and dark energy in the expansion of the universe, and it helps to refine our models of how galaxies form and evolve. One of the most intriguing possibilities in modern astrophysics is the idea that black holes might not be as final as we once thought. Some theories propose that black holes could act as gateways to other regions of space-time, or even other universes. This concept is often explored through the idea of wormholes, which could theoretically connect distant points in the universe through a tunnel-like structure. While such ideas remain in the realm of speculation, they challenge our understanding of what happens inside black holes and whether space-time has a structure that is more interconnected than we can perceive. If wormholes exist, they might offer a pathway for future space travelers to explore distant regions of the universe in ways that are currently unimaginable, turning science fiction into a tantalizing possibility. In the realm of galactic evolution, we are learning that galaxies themselves can transform dramatically over time. For instance, quenching is a process where galaxies stop forming new stars, often due to interactions with other galaxies or the effects of supermassive black holes. When a black hole at the center of a galaxy becomes active, it can emit jets of energy that heat up the surrounding gas, preventing it from cooling and condensing into new stars. This process can turn a once vibrant, star-forming galaxy into a red and dead elliptical galaxy, dominated by older stars. Understanding why some galaxies undergo quenching while others remain active is a key question in the study of galactic life cycles, shedding light on how the universe's grand structures evolve and change over billions of years. On the cutting edge of space technology, the development of artificial gravity through rotating habitats offers a potential solution to one of space travel's biggest challenges: the effects of microgravity on human health. By creating a spinning space station or spaceship, centrifugal force could simulate gravity, helping astronauts maintain muscle mass and bone density during long-term missions. Concepts like the O'Neill cylinder, a massive rotating habitat proposed by physicist Gerard K. O'Neill, envision entire colonies in space where people could live and work in a gravity-like environment. These ideas, while still theoretical, represent a potential path forward for sustainable human presence in space, allowing for the creation of space settlements that could support life beyond Earth for extended periods. As we continue to chart the cosmos, we are also learning more about the history of our own solar system, particularly through the study of Kuiper Belt objects. Beyond Neptune, The Kuiper Belt is a region filled with icy bodies and dwarf planets like Pluto, providing a snapshot of the solar system's early days. Missions like New Horizons, which flew by Pluto in 2015 and later visited the distant object Arrokoth, have revealed that these frozen worlds can be surprisingly complex, with varied geology and a history shaped by collisions and orbital dynamics. Studying Kuiper Belt objects helps us understand the processes that shape the outer reaches of our solar system and the conditions that existed as the Sun and planets first formed. Finally, as we look out to the stars, we are faced with the paradox of the Great Silence, also known as the Fermi Paradox. Despite the vastness of the universe and the likelihood that life could arise on many planets, we have yet to find any definitive signs of intelligent extraterrestrial civilizations. This raises profound questions. If life is common, where is everyone? Some suggest that intelligent civilizations might be self-destructing before they reach the capability of interstellar communication. Others propose that advanced societies might choose to remain hidden, preferring not to interact with less advanced life forms. Another possibility is that we are simply looking in the wrong way or at the wrong times, and that the universe is teeming with life forms that communicate using technologies beyond our understanding. The search for answers to the Fermi paradox drives projects like the SETI, Search for Extraterrestrial Intelligence, and encourages us to think about our place in the cosmos in new and humbling ways. As the boundaries of space and time expand with each new discovery, we are reminded that the universe is far stranger and more beautiful than we ever imagined. From the hidden depths of black holes to the icy oceans of distant moons, from the vast emptiness of supervoids to the whispers of gravitational waves, the cosmos offers endless mysteries. Our journey through space is more than just a quest for knowledge. It's a celebration of the curiosity that defines us as a species, a testament to our desire to understand the world around us. Even as we explore the most distant galaxies, we are really searching for answers to some of the most fundamental questions. Are we? Where do we come from? And what will we become in this vast, mysterious universe that we call home? Each discovery brings us a little closer to understanding, while reminding us that the adventure of exploration is, in many ways, just beginning. As our exploration of the cosmos continues, we find ourselves at the crossroads of some of the most profound questions ever asked by humanity. The mysteries of space invite us to reconsider not only our place in the universe, but the very nature of existence itself. One of the most captivating concepts is the idea of quantum fluctuations in the vacuum of space. These fluctuations suggest that even empty space can produce particles spontaneously, borrowing energy from the void for incredibly brief moments before they disappear again. This concept is central to the theory of quantum foam, which envisions space-time itself as a frothy, chaotic sea at the smallest scales, where distances as tiny as the Planck length, about /10⁻⁻35 meters, are subject to constant, roiling change. It's a realm where the fabric of reality flickers between existence and non-existence, and where the smooth continuum of space-time gives way to a more granular and dynamic reality. This insight pushes us to question whether space-time, as we perceive it, is the ultimate framework, or merely an emergent property of deeper, more fundamental forces at play. Quantum foam also leads to fascinating discussions about the holographic principle, a theory suggesting that all the information contained within a three-dimensional volume of space could be encoded on a two-dimensional surface, like a hologram. This idea, which arises from studies of black holes and string theory, proposes that our entire universe might be akin to a holographic projection, with the real information encoded on a boundary far away. If true, it could radically alter our understanding of reality, hinting that the three-dimensional world we experience is a kind of illusion, a shadow of a deeper, more fundamental reality. This concept is especially relevant in attempts to understand what happens at the event horizons of black holes, where the laws of quantum mechanics and general relativity appear to clash. The holographic principle might offer a path to reconciling these laws, suggesting that the universe is stranger and more layered than our senses suggest. As we venture beyond the theoretical, our study of the early universe has provided crucial insights into how the cosmos evolved from a hot, dense state into the vast, structured universe we see today. One of the key periods in this transformation is reionization, which occurred about 400 million years after the Big Bang. During this time, the first stars and galaxies ignited, emitting ultraviolet light that reionized hydrogen atoms in the intergalactic medium, turning it from a neutral gas into a charged plasma. This era marks the dawn of the universe, when darkness gave way to light and the first structures began to shape the cosmos. Observing this period is a challenge, as the light from these early stars is faint and redshifted due to the expansion of the universe. However, telescopes like the James Webb Space Telescope (JWST) are beginning to pierce this veil, providing a window into the universe's first billion years. These observations help us understand the formation of the first galaxies and black holes, offering a glimpse into the conditions that set the stage for everything that followed. In studying the universe's large-scale structure, scientists have uncovered patterns that resemble a cosmic web, a vast, interconnected network of galaxies, galaxy clusters, and dark matter filaments spanning across billions of light years. This structure, known as the cosmic web, reveals how matter in the universe is organized, with galaxies forming along dense filaments while vast voids exist between them. The cosmic web structure is shaped by the interplay between dark matter and gravity, guiding the growth of galaxies and clusters over billions of years. It's a reminder that the universe is not random, but follows underlying principles that govern how matter and energy flow through space. By mapping the cosmic web using surveys like the Sloan Digital Sky Survey (SDSS), scientists can trace the evolution of the universe from the Big Bang to the present day, providing insights into how gravity and dark matter have sculpted the universe's intricate patterns. Closer to Earth, the study of magnetars, a type of neutron star with magnetic fields 1,000 trillion times stronger than Earth's, offers a glimpse into some of the most extreme conditions in the universe. These magnetic fields are so intense that they can warp atoms into pencil-thin shapes and cause starquakes, massive bursts of energy that release as much power as the sun would emit in 100,000 years, all in a matter of seconds. Magnetars are believed to form when the core of a massive star collapses during a supernova, creating a rapidly spinning neutron star with a powerful magnetic field. The immense energy of magnetars makes them fascinating objects to study, particularly because they may also produce mysterious fast radio bursts, FRBs, which are intense flashes of radio waves that have puzzled astronomers since their discovery. Understanding magnetars and their extreme environments could provide clues about how matter behaves under conditions that cannot be replicated on Earth, offering insights into the fundamental forces that govern the universe. As we look further into the universe, we encounter the concept of cosmic strings, hypothetical, one-dimensional defects in space-time that could have formed during the early universe. These strings, thinner than an atom, yet immensely dense, could stretch across the universe, acting like invisible scars left behind from the universe's birth. If they exist, cosmic strings could create gravitational waves as they oscillate and interact, producing ripples in space-time detectable by advanced observatories. Some theories suggest that these strings could even form loops that decay over time, releasing energy in bursts. While cosmic strings remain speculative, their existence would provide a fascinating link between cosmology and particle physics, offering a glimpse into the universe's most fundamental structure. Detecting such strings would be akin to discovering ancient fossils from the dawn of time, preserving information about conditions that existed just moments after the Big Bang. In our search for life beyond Earth, the concept of biosignatures has become central to the study of exoplanets. Biosignatures are chemical markers in a planet's atmosphere or surface that could indicate the presence of life. Methane, oxygen, and even certain complex organic molecules are considered potential biosignatures when found in the right balance. For instance, on Earth, methane is primarily produced by biological processes, so finding methane alongside other gases like oxygen in an exoplanet's atmosphere could hint at biological activity. As the James Webb Space Telescope and other observatories begin to characterize the atmospheres of rocky planets in the habitable zones of their stars, the detection of biosignatures becomes a tantalizing possibility. Such a discovery would profoundly change our understanding of life's potential distribution in the universe, suggesting that life could be more common than previously thought, existing wherever the right conditions are met. But the search for life is not limited to distant exoplanets. Recent studies have revealed that even Venus, long considered inhospitable due to its scorching surface temperatures and crushing atmosphere, might have the potential for life in its upper clouds. In 2020, scientists detected traces of phosphine gas in the cloud layers of Venus, a compound that, on Earth, is often associated with biological processes. While the detection is debated and the origins of the phosphine remain uncertain, the discovery has renewed interest in studying Venus, suggesting that life could survive in more extreme conditions than we once imagined. Future missions to Venus, such as NASA's Da Vinci Plus and Veritas, aim to explore its atmosphere and surface in more detail, searching for signs that microbial life could exist in the temperate layers of its thick, acidic clouds. These missions underscore the idea that life might adapt to a wide range of environments, thriving in places previously considered uninhabitable. The study of supermassive black holes at the centers of galaxies, including our own Milky Way's Sagittarius A*, continues to reveal new insights into the dynamic interactions between black holes and their surrounding environments. Supermassive black holes are millions to billions of times more massive than our Sun, and their influence extends far beyond their event horizons, affecting the formation of stars and the evolution of their host galaxies. When these black holes actively accrete matter, they form quasars, extremely luminous objects that can outshine entire galaxies. These powerful engines emit jets of plasma that travel at near light speeds, shaping the interstellar medium and regulating star formation in their host galaxies. Observations of quasars and their interactions with surrounding gas provide a window into the growth of black holes and their role in shaping the cosmic landscape over billions of years. As we strive to understand the mysteries of dark energy, the question of whether the universe will continue to expand indefinitely or eventually reverse course in a big crunch remains open. Another possibility is that dark energy could lead to a scenario known as the Big Rip, where the universe's expansion accelerates to the point that galaxies, stars, planets, and even atomic structures are torn apart. This scenario would mark a dramatic end to the universe, dissolving the very fabric of space-time itself. Yet other models suggest a gentler fate, where the universe's expansion slows down over time, reaching a stable state in a big chill or heat death, where all activity ceases as stars burn out and black holes evaporate. The ultimate fate of the universe depends on the nature of dark energy, a mystery that remains at the forefront of cosmological research, guiding us in our quest to understand the long-term evolution of everything that exists. In exploring these cosmic mysteries, we are reminded that the universe is a vast and dynamic place, where the smallest particles can alter the course of stars, and the largest structures hint at hidden dimensions beyond our reach. Each discovery, from the faint whisper of gravitational waves to the potential signs of life in distant atmospheres, adds to our understanding of a cosmos that is rich with possibilities and challenges. The journey through space and time is one of constant surprise, where every answer leads to new questions, and every new question deepens our sense of wonder. As we look beyond the stars, we continue to seek not only knowledge, but a deeper connection to the universe that made us. A reminder that in the grand story of the cosmos, we are both observers and participants, explorers on a voyage with no end in sight. As we journey deeper into the cosmos, the boundaries of our understanding continue to expand, revealing astonishing phenomena that challenge the very fabric of our reality. One of the most awe-inspiring concepts in cosmology is cosmic inflation, a rapid expansion that occurred in the universe's first moments, just a fraction of a second after the Big Bang. During this brief but intense phase, the universe ballooned from subatomic scales to a size much larger than the observable universe today. This rapid growth smoothed out irregularities, resulting in the uniformity of the cosmic microwave background radiation we see today. However, the inflationary model also suggests that the universe could be part of a much larger multiverse, where inflation caused different regions to expand into separate, bubble-like universes, each with its own set of physical laws. This raises the profound possibility that our universe is just one of countless others, each with unique properties and constants. The multiverse theory intersects with the study of string theory, which posits that the fundamental particles of nature are not point-like dots, but tiny, vibrating strings of energy. These strings vibrate in multiple dimensions beyond the familiar 3 dimensions of space and 1 of time, suggesting that our universe could be a brain floating within a higher dimensional space. According to string theory, the collision of brains could even explain the Big Bang itself, where the impact of 2 such brains created the energy and matter that make up our universe. While experimental evidence for string theory remains elusive, it offers a tantalizing framework for understanding how gravity fits with quantum mechanics, potentially leading to a theory of everything, a single, elegant description that unites all known forces and particles. As we study the fabric of space-time itself, we encounter the intriguing concept of virtual particles and their role in quantum vacuum fluctuations. These particles constantly appear and disappear in pairs, creating a background hum of energy even in what we think of as empty space. While they exist for only fleeting moments, virtual particles can have real effects, such as generating the Casimir effect, where 2 uncharged metal plates placed close together in a vacuum experience an attractive force due to the restricted quantum fluctuations between them. This demonstrates that the vacuum is not truly empty, but filled with potential energy, a concept that has significant implications for our understanding of dark energy. If virtual particles contribute to the vacuum energy, they could help explain the mysterious force that is driving the universe's accelerated expansion, suggesting that the quantum world might have a profound influence on the cosmos. The study of black holes has led to discoveries that continue to defy our understanding of physics. One of the most fascinating aspects of black holes is the event horizon, the boundary beyond which nothing, not even light, can escape. But recent research suggests that black holes might not be as simple as they seem. The theory of firewalls proposes that the event horizon could be surrounded by a searing wall of energy that incinerates anything that comes too close, challenging the idea of a smooth, empty space at the edge of a black hole. This theory has sparked debates about whether information that falls into a black hole is truly lost or if it can be preserved in some form. Resolving these questions is critical for understanding the information paradox, a clash between quantum mechanics, which suggests that information must be preserved, and general relativity, which seems to allow information to disappear into a black hole's depths. The solution to this paradox could hold the key to a deeper understanding of space, time, and the very nature of reality. The interior of black holes remains one of the most mysterious places in the universe, especially the region known as the singularity, where gravity becomes infinitely strong and space-time curves infinitely. General relativity breaks down at this point, unable to describe what happens beyond it. Some theories suggest that singularities might be portals to other universes, or that they could be replaced by a Planck star, a hypothetical object where quantum effects resist further collapse, preventing the formation of a true singularity. Understanding what happens inside a black hole could provide insights into the nature of space-time at the smallest scales and help us develop a theory of quantum gravity, uniting the principles of quantum mechanics with those of general relativity. This quest to understand the singularity is one of the great challenges of modern physics, pushing the boundaries of both theoretical and observational science. As we look for signs of life beyond Earth, the discovery of biosignatures on exoplanets has become a central focus of astrobiology. With the deployment of the James Webb Space Telescope, scientists are now able to probe the atmospheres of distant worlds in greater detail than ever before, searching for chemical markers that might indicate biological processes. For instance, the simultaneous presence of oxygen and methane in an exoplanet's atmosphere could suggest biological activity, as these gases would otherwise react with each other and be depleted over time. However, the challenge lies in distinguishing these signals from abiotic processes, those that do not involve life. To increase the chances of finding extraterrestrial life, astronomers are focusing on M-dwarf stars, which are the most common type of star in the galaxy and often host planets in their habitable zones. These smaller stars burn cooler and longer than stars like our Sun, making their habitable zones closer and potentially more stable for life over long periods. The outer solar system also holds intriguing possibilities for life, particularly on icy moons like Europa and Enceladus. These moons, with their subsurface oceans, could harbor microbial life in environments similar to Earth's deep-sea hydrothermal vents. NASA's upcoming Europa Clipper mission aims to fly through the plumes of water vapor erupting from Europa's icy surface, analyzing their composition for organic molecules that could hint at biological activity. Meanwhile, the Dragonfly mission will explore the surface of Titan, Saturn's largest moon, which has lakes of liquid methane and ethane. Titan's thick atmosphere and complex organic chemistry make it a prime candidate for studying prebiotic conditions that might resemble those of early Earth. The search for life in these distant oceans could provide answers to fundamental questions about the potential for life in environments far different from our own. As we contemplate the fate of the universe, scientists have proposed several scenarios, each offering a different vision of how everything might end. One such possibility is the Big Crunch, where the expansion of the universe eventually slows and reverses, causing the cosmos to collapse back into a hot, dense state, potentially leading to another Big Bang. Another idea is the heat death or Big Chill, where the universe continues to expand forever, gradually cooling as stars burn out and black holes slowly evaporate through Hawking radiation, leaving a dark, empty cosmos filled with nothing but diffuse particles. Yet, a more dramatic scenario is the Big Rip, in which dark energy's influence increases over time, causing galaxies, stars, planets, and even atomic structures to be torn apart. This would result in a universe that disintegrates into its most basic components, with space-time itself unraveling. Each of these scenarios highlights the complex interplay between gravity, dark energy, and the underlying structure of the universe, reminding us of the profound mysteries that remain about the forces shaping our cosmic destiny. In the quest to understand the universe's ultimate fate, scientists have turned to the study of ancient light to probe its earliest moments. The cosmic microwave background, CMB, a relic of the Big Bang, offers a snapshot of the universe when it was just 380,000 years old, a time when photons first escaped the hot plasma that filled space, allowing light to travel freely. By studying the tiny temperature fluctuations in the CMB, astronomers have mapped the universe's initial conditions with incredible precision, revealing the seeds that grew into galaxies and clusters. These observations have confirmed the existence of dark matter and dark energy, providing a cornerstone for our current cosmological models. Yet, mysteries remain, such as the anisotropies, small variations in temperature across the CMB that hint at processes in the very early universe that we do not yet fully understand. These subtle signals could hold clues about inflation, the nature of dark matter, or even the influence of other universes, making the study of the CMB a window into the universe's deepest secrets. Back in our own solar system, we continue to uncover surprises in unexpected places. The dwarf planet Ceres, located in the asteroid belt between Mars and Jupiter, was found to have bright spots on its surface, later identified as deposits of sodium carbonate, a type of salt. These spots, visible on the cratered surface of Ceres, suggest that the dwarf planet might have once had a subsurface ocean, raising the possibility that it could still retain pockets of liquid water today. Such findings challenge our assumptions about where life might exist, suggesting that even small, cold bodies like Ceres could hold the potential for habitability. As we explore these icy worlds, we are reminded that life's possibilities might extend beyond Earth-like conditions, thriving in environments that we once thought barren. The Kuiper Belt, home to a multitude of icy objects beyond Neptune, continues to be a frontier of discovery, revealing worlds like Arrokoth, which was visited by the New Horizons mission after its historic flyby of Pluto. Arrokoth, with its two lobes that appear to have gently merged, provides insights into how planetesimals, the building blocks of planets, formed in the early solar system. Studying such objects helps us understand the processes that shaped our planetary neighborhood billions of years ago, offering clues about how Earth and the other planets came to be. As we probe deeper into the Kuiper Belt, we are uncovering the remnants of the solar system's ancient history, frozen in time at the far edge of our sun's domain. Through each new discovery, we find that the universe is not only a place of incredible size, but also of intricate complexity and surprising connections. From the smallest quantum fluctuations to the grand arcs of galaxy clusters, the cosmos presents a tapestry of phenomena that challenge our understanding and expand our sense of what is possible. As we continue to explore, we are reminded that the journey of discovery is as much about asking the right questions as it is about finding answers. The universe, with its myriad wonders, remains a vast and open book, and we are only beginning to turn its pages, uncovering the secrets written in the light of distant stars and the whispers of ancient galaxies. It is a story that stretches back to the dawn of time and forward into a future we are still learning to imagine. In this grand adventure, the stars are not just distant beacons but signposts guiding us toward a deeper understanding of the cosmos and of ourselves. As our exploration of the universe stretches further into the unknown, we begin to consider concepts that seem almost too strange to be real, yet they arise naturally from the mathematics of modern physics. One such concept is negative energy, a hypothetical form of energy that could allow for phenomena like wormholes and even time travel. Negative energy is not something we encounter in everyday life, but it appears in certain solutions to Einstein's equations of general relativity and in theories involving exotic matter. A wormhole, for instance, would require negative energy to remain open, creating a shortcut through space-time that could connect distant regions of the universe. While negative energy remains speculative and beyond our current ability to harness, it captures the imagination, offering a glimpse into how the universe might have shortcuts hidden within its vast expanse, potentially allowing for faster-than-light travel. The concept of tachyons, particles that could travel faster than light, also arises from the realms of theoretical physics. Tachyons would have the peculiar property of increasing in energy as they slow down, making them entirely different from ordinary particles. Their existence would violate the known laws of physics, particularly the theory of relativity, which holds that nothing can exceed the speed of light. Yet, the idea of tachyons has been explored as a mathematical curiosity, hinting at the possibility that the universe might contain phenomena that transcend our current understanding of space-time. While no evidence for tachyons has been found, their theoretical existence forces us to ask whether there could be aspects of the cosmos that operate beyond the limits of light speed, suggesting that our universe might have layers of reality yet to be uncovered. As we study the grand structures of the cosmos, we encounter the concept of dark flow, an unexplained motion of galaxy clusters toward a particular region of the sky. This mysterious drift was first observed using data from the Cosmic Microwave Background, CMB, revealing that clusters of galaxies are moving in a consistent direction at speeds much faster than expected from known gravitational influences. Some scientists speculate that dark flow could be evidence of structures beyond the observable universe, perhaps other regions of space-time that exert a gravitational pull on our own cosmic bubble. If true, it would mean that our observable universe is part of a much larger, more complex structure, where unseen regions influence the movement of galaxies. The study of dark flow remains one of the most tantalizing questions in cosmology, challenging the boundaries of what we can observe and understand about the universe's large-scale dynamics. In the realm of black holes, the idea of spinning black holes, or Kerr black holes, introduces new dimensions to our understanding of these cosmic giants. Unlike static black holes, spinning black holes have angular momentum, causing space-time around them to twist and swirl in a phenomenon known as frame dragging. This effect means that anything approaching a spinning black hole is caught in a whirlpool of space-time, potentially making it possible to travel around the event horizon without being pulled in immediately. Theoretical models suggest that Kerr black holes could even possess regions called ergospheres, where space-time is dragged faster than the speed of light. Inside the ergosphere, it might be possible for particles to escape with more energy than they entered, leading to speculative ideas about extracting energy from black holes. This process, known as the Penrose process, remains a theoretical curiosity, but it hints at the complex interactions between matter, energy, and the warped fabric of space-time. The concept of quantum entanglement also challenges our understanding of space and time, especially when applied to the vast scales of the universe. When two particles become entangled, their states are linked so that a change in one instantly affects the other, regardless of the distance between them. This phenomenon, which Einstein famously referred to as spooky action at a distance, has been experimentally confirmed on microscopic scales. But what if this form of connection extends across cosmic distances? Some theories propose that the entanglement between particles might help explain the mysterious phenomenon of quantum gravity, suggesting that space-time itself could emerge from a network of entangled particles. In this view, the fabric of the universe might be more akin to a web of quantum connections, with the geometry of space-time being a result of these deep, hidden links. This approach could offer a path toward uniting general relativity with quantum mechanics, bringing us closer to understanding the fundamental nature of reality. In the study of the universe's beginning, the concept of the pre-Big Bang state remains one of the greatest mysteries. While the Big Bang theory describes how the universe expanded from an incredibly hot and dense state, it does not explain what triggered this event or what came before it. Some theories suggest that the universe could have emerged from a quantum fluctuation in a state of nothingness, where the laws of physics as we know them didn't yet apply. Other models propose that our universe might be part of a cyclical process, where each Big Bang is followed by a period of expansion, cooling, and eventual collapse, leading to a new Big Bang, a cosmic rebirth. These ideas challenge the traditional concept of time itself, suggesting that time might not be a straight line, but rather a loop, or even something more complex. The pre-Big Bang theories push the limits of our understanding, offering tantalizing hints at a reality that is far more intricate than the universe we observe today. As we look beyond the visible cosmos, we find that the search for dark matter remains a critical focus of modern astrophysics. While dark matter is known to make up about 27% of the universe's total mass energy content, its true nature is still a mystery. Some theories suggest that dark matter could be composed of WIMPs, weakly interacting massive particles, hypothetical particles that rarely interact with normal matter except through gravity. Others propose that dark matter could be made up of axions, incredibly light particles that could also solve certain problems in particle physics. Yet, despite extensive searches using particle detectors deep underground and powerful particle accelerators like the Large Hadron Collider, direct evidence of these particles remains elusive. Another possibility is that dark matter is not a particle at all, but a manifestation of deviations from general relativity on large scales, a concept known as modified gravity. If dark matter is indeed something more fundamental, it could reveal new physics beyond the standard model, reshaping our understanding of the universe's most fundamental forces. The search for dark matter has also led to the discovery of dark galaxies, hypothetical galaxies that contain little to no visible stars but are rich in dark matter. These ghostly structures are thought to exist in regions where dark matter dominates, preventing gas from cooling and forming stars. While difficult to detect directly, scientists have found evidence for dark galaxies through their gravitational effects on nearby objects, such as distortions in the movement of stars and the bending of light through gravitational lensing. If dark galaxies are confirmed, they would provide a unique window into the dark side of the universe, offering clues about how dark matter behaves and clusters on different scales. Understanding these dark structures could help explain why certain regions of space are devoid of visible matter, shedding light on the hidden architecture of the cosmos. As we explore the universe's extremes, the study of superfluidity in neutron stars has revealed surprising behavior under conditions of intense pressure and gravity. Neutron stars, the remnants of massive stars that have collapsed under their own gravity, can contain cores where neutrons form a superfluid, a state of matter with zero viscosity that flows without losing energy. In such conditions, the interior of a neutron star might rotate differently than its outer crust, leading to sudden changes in rotation speed known as glitches. These glitches provide valuable insights into the exotic matter that exists inside neutron stars, revealing how the strong nuclear force behaves under extreme densities. By studying these bizarre states of matter, scientists can better understand the physics of neutron stars and the conditions that prevail in the universe's densest objects. In the context of our own solar system, the search for Planet 9 continues to capture the imagination of astronomers. This hypothetical planet, believed to be much larger than Earth, could be lurking in the far reaches of the solar system, beyond the Kuiper Belt. Its existence was proposed to explain the unusual orbits of several distant, icy objects, which appear to be clustered in a way that suggests the gravitational influence of a massive object. If Planet 9 exists, It would represent a new class of planet, challenging our understanding of the solar system's formation and structure. Despite extensive searches using some of the world's most powerful telescopes, Planet 9 has yet to be directly observed, leaving its existence an open question. Finding it would redefine our view of the solar system, adding a new chapter to the story of planetary discovery. In the study of exoplanets, the discovery of rogue planets, planets that do not orbit any star, has expanded our understanding of the diversity of planetary systems. These free-floating worlds are thought to have been ejected from their star systems due to gravitational interactions, drifting through the galaxy like cosmic nomads. Some estimates suggest that there could be more rogue planets than stars in the Milky Way, meaning that these wandering worlds might be common. If they have thick atmospheres or internal heat sources, some rogue planets could even sustain subsurface oceans, offering the intriguing possibility that life could exist in these starless environments. The study of rogue planets challenges our traditional notions of habitability, suggesting that life might find a way in places we never thought to look. Each new discovery in the cosmos adds another layer to our understanding, showing us that the universe is not only vast, but also filled with strange possibilities and hidden wonders. From the potential of negative energy and wormholes to the mysteries of dark flow and the ghostly presence of dark galaxies, the cosmos continues to surprise and inspire. As we push the boundaries of observation and theory, we are reminded that the universe is a place of endless mystery, where every answer leads to new questions. It is this sense of wonder and curiosity that drives us to explore, to look beyond the limits of what we know, and to seek out the hidden truths that lie in the stars. In the grand tapestry of existence, we are but a small thread, yet we are woven into a story that stretches across space and time, a story that is still being written with every new discovery and every new question that arises from the depths of the cosmos. As we venture even further into the cosmos, we encounter concepts that stretch the limits of our imagination, suggesting that the universe is a place where reality itself bends in unexpected ways. One of the most compelling of these ideas is the concept of cosmic strings, hypothetical defects in space-time that might have formed during the early universe. These one-dimensional objects could stretch across vast distances, thinner than a proton, yet incredibly dense, capable of bending light and distorting space-time around them. If they exist, cosmic strings could create observable effects, such as gravitational lensing, where light from distant galaxies is warped into arcs and rings as it passes near these strings. Detecting such structures would provide a direct link to the conditions of the universe shortly after the Big Bang, revealing a snapshot of the primordial forces that shaped the cosmos. Another mind-bending concept is that of Boltzmann brains, hypothetical self-aware entities that could randomly form in a universe governed by entropy and thermodynamic fluctuations. The idea stems from the notion that in an infinitely old or infinitely large universe, given enough time, a brain, complete with memories and consciousness, could spontaneously emerge from random fluctuations of particles. While it's an unlikely and bizarre proposition, the concept raises deep philosophical questions about consciousness, reality, and the nature of existence. It suggests that if the universe were truly infinite, the emergence of such entities might be more common than life arising through evolution on planets like Earth. Boltzmann brains challenge our understanding of what it means to be conscious and whether our perception of reality is rooted in a universe that follows familiar physical laws or in a more surreal, probabilistic landscape. As we delve into the mysteries of the universe's expansion, we encounter the enigmatic cosmic acceleration, driven by a force known as dark energy. This phenomenon, discovered in the late 1990s, revealed that not only is the universe expanding, but the rate of expansion is increasing over time. Dark energy acts as a sort of anti-gravity, pushing galaxies apart faster and faster, leading to the idea that space itself has an intrinsic energy that increases as it expands. Some scientists propose that dark energy could be a manifestation of the cosmological constant, a term originally introduced by Einstein, or it could be due to a new type of energy field known as quintessence. The exact nature of dark energy remains one of the greatest mysteries in physics, as understanding it would not only explain the fate of the universe, but could also provide insights into the fundamental nature of space and time. One of the most striking discoveries related to the universe's expansion is the presence of voids, vast regions of space where few galaxies or stars exist. These cosmic voids, some spanning hundreds of millions of light years, contrast sharply with the dense clusters and filaments that make up the cosmic web. While these voids might seem like empty, desolate places, they are crucial to understanding the large-scale structure of the universe. The study of voids helps scientists learn about the distribution of dark matter and the way galaxies form and evolve over cosmic time. Observing how galaxies near the edges of voids interact and move provides clues about the gravitational forces at work on a grand scale. Voids also serve as a kind of natural laboratory for studying dark energy, as their expansion rates can offer insights into how dark energy influences different parts of the universe. In the quest to understand the geometry of the universe, scientists have proposed different models to describe its shape. The universe could be flat, meaning that parallel lines never converge or diverge, and its fate would be determined by the balance between gravity and dark energy. Alternatively, the universe could be open, with a hyperbolic geometry that causes space to curve away from itself, leading to endless expansion. Or it could be closed like a three-dimensional sphere, where space eventually loops back on itself. The current evidence from the cosmic microwave background and large-scale structure surveys suggests that the universe is nearly flat, but with a slight curvature that remains difficult to measure precisely. Understanding the geometry of the universe helps us determine its ultimate fate and whether it might have boundaries or be infinite in extent. One of the most peculiar ideas in modern cosmology is the concept of a Big Bounce, an alternative to the traditional Big Bang model. The Big Bounce suggests that our universe could have emerged from the collapse of a previous universe, undergoing a cycle of contraction and expansion. In this model, the universe never reaches a singularity, an infinitely small point of density, but instead bounces back as quantum effects counteract the gravitational collapse. This cyclical nature implies that the universe could be eternal, with each big bounce giving birth to new cosmic epochs, each with its own stars, galaxies, and physical conditions. While evidence for such a model remains elusive, the Big Bounce provides a compelling framework for thinking about the origins of the universe, offering a way to avoid the mysteries associated with the initial singularity and providing a more continuous view of cosmic evolution. The study of supermassive black holes continues to reveal surprising phenomena, including the potential existence of ultramassive black holes, which are far larger than the already gargantuan black holes at the centers of galaxies. These monsters, which could weigh tens of billions of times the mass of our Sun, are thought to form through the merger of galaxies and the accumulation of matter over billions of years. Observations of the brightest quasars, powered by matter falling into such black holes, suggest that they could have existed even in the early universe, only a few 100 million years after the Big Bang. The existence of ultramassive black holes challenges our understanding of how quickly structures can form in the cosmos, pushing scientists to rethink models of galaxy evolution and the growth of black holes. These objects are not just cosmic curiosities. They play a crucial role in shaping the galaxies around them, influencing star formation and the distribution of matter through powerful jets and outflows. Meanwhile, the discovery of gravitational waves has opened a new window into the universe, allowing us to observe the most violent events in space, like the collisions of black holes and neutron stars. Gravitational waves are ripples in the fabric of space-time, generated by accelerating massive objects, and they travel across the cosmos, carrying information about their sources. Since the first detection by LIGO in 2015, dozens of gravitational wave events have been observed, providing insights into the population of black holes in the universe and the nature of neutron stars. These observations have even allowed scientists to confirm the existence of binary neutron star mergers, which produce both gravitational waves and electromagnetic signals, offering a new way to study the production of heavy elements like gold and platinum. The era of multi-messenger astronomy, combining data from gravitational waves, light, and neutrinos, has transformed our ability to probe the universe, revealing processes that were once beyond our reach. As we look deeper into the cosmos, we encounter the idea of primordial black holes, small black holes that might have formed directly from the extreme conditions of the early universe, rather than from the collapse of stars. These objects could range in size from microscopic to several times the mass of the Sun. Some theories even suggest that primordial black holes could make up a portion of dark matter, offering a possible explanation for its elusive nature. While no direct evidence for primordial black holes has been found, searches continue through studies of gravitational lensing, the cosmic microwave background, and even the distribution of stars in the Milky Way. If they exist, primordial black holes could provide a unique window into the conditions of the universe just moments after the Big Bang, revealing how space-time itself behaved under the most extreme conditions imaginable. The Fermi paradox remains one of the most profound questions in the search for extraterrestrial life. If intelligent life is likely in a vast universe filled with habitable planets, why have we not detected any signs of other civilizations? Some proposed solutions suggest that life might be common, but intelligent life is rare, or that advanced civilizations might choose to remain silent, avoiding detection. Others speculate about the existence of a great filter, a stage of development that is extremely difficult to surpass, such as the leap from simple to complex life or the challenge of avoiding self-destruction. The Fermi paradox has also led to the concept of technosignatures, signals or artifacts that might indicate advanced technology. Projects like the Breakthrough Listen initiative are scanning the skies for radio signals or unusual patterns that might suggest the presence of technological civilizations. The search for answers to the Fermi paradox drives our efforts to explore beyond our planet, as we try to determine whether we are truly alone in the cosmos or part of a broader tapestry of life. As we continue our journey of exploration, the boundaries between the known and the unknown blur, revealing a universe that is as strange as it is beautiful. Each new observation, from the bending of light around distant objects to the ripples of space-time passing through our detectors, offers a glimpse into a cosmos filled with phenomena that challenge our understanding. It is a place where time loops back on itself, where space can stretch and warp, and where reality seems to play by rules that defy our everyday experiences. Yet, for all its mysteries, the universe also tells a story of stars born in clouds of gas, of galaxies colliding and merging, of life arising from stardust on a small blue planet. It is a story that we are a part of, and one that we continue to write with each new discovery, each new question we dare to ask. In this vast and mysterious universe, our quest for knowledge is not just about finding answers, but about embracing the unknown, seeking out the hidden wonders that lie just beyond the horizon. As we venture deeper into the vast expanse of the universe, we find that each discovery reveals a cosmos far more complex and intricate than we ever imagined. Among the most intriguing concepts in modern astrophysics is the idea of white holes. These theoretical objects are the time-reverse counterparts of black holes. While a black hole is a region of space where gravity is so intense that nothing can escape from it, a white hole would be a region from which matter and energy can only exit and nothing can enter. In theory, white holes could expel matter that was once inside a black hole, almost like a cosmic fountain ejecting material back into the universe. While no direct evidence of white holes has been found, they are solutions to Einstein's equations of general relativity, suggesting that under certain conditions, such exotic structures might be possible. The idea of a universe containing white holes hints at a deeper and more mysterious nature of space-time, where the life cycle of a black hole might not be an endpoint, but a transition to something altogether different. The possibility that black holes could serve as gateways to other parts of the universe, or even to other universes, remains a topic of fascination and speculation. Some theories, like those involving wormholes, suggest that the singularity inside a black hole might be connected to another region of space-time through a tunnel-like structure. These wormholes, if they exist, could provide shortcuts across vast distances, potentially allowing for faster-than-light travel. However, the stability of such wormholes remains a significant challenge. Most solutions indicate that they would collapse almost instantly unless held open by exotic forms of negative energy. If a black hole singularity could be connected to a white hole through a wormhole, it would create a structure known as an Einstein-Rosen bridge. While such ideas remain purely theoretical, they fuel the imagination and push the boundaries of what we consider possible in our universe. The study of cosmic inflation has also led to the idea that our universe might be part of an eternal inflationary multiverse. In this model, inflation never stops entirely. Instead, it continues in some regions of space, creating new pocket universes with varying properties and physical constants. Each of these universes could have different laws of physics, creating a vast landscape of possible realities, some similar to our own and others fundamentally different. The process of eternal inflation suggests that our universe is like a bubble within a frothy sea of other bubbles, each representing a different universe with its own story. This idea challenges our understanding of what constitutes the universe and our place within it, suggesting that the observable cosmos might be just a small part of a far larger and more diverse multiverse. As we probe the depths of the cosmos, we encounter the concept of vacuum decay, a chilling possibility that arises from the study of quantum fields. Our universe might exist in a state known as a false vacuum, a condition that is stable for now but could eventually decay into a more stable state. This transition, known as vacuum decay, could occur spontaneously, creating a bubble of true vacuum that expands at the speed of light, annihilating everything in its path. Such a bubble would alter the fundamental constants of physics, making the universe as we know it uninhabitable. While vacuum decay is a speculative concept, it highlights the precarious nature of reality, reminding us that even the stability of space itself might be subject to change. Yet, the timescales involved in such processes are likely far beyond the age of the universe, offering both a sense of cosmic awe and an unsettling reminder of the universe's potential for sudden change. Closer to home, the study of Oumuamua, the first known interstellar object to pass through our solar system, has raised intriguing questions about the nature of objects from beyond our stellar neighborhood. When Oumuamua was discovered in 2017, its elongated shape and unusual acceleration puzzled scientists, leading to speculation about its origin. Some propose that it could be a fragment of a shattered planet or a cometary object that had been stripped of its outer layers during its journey through interstellar space. Others suggested more exotic possibilities, including the idea that it might be an artificial probe sent by an alien civilization, although no evidence supports this claim. Oumuamua's strange characteristics have made it a symbol of the mysteries that lie beyond our solar system, reminding us that our understanding of what exists between the stars is still in its infancy. The possibility of exomoons, moons orbiting planets outside our solar system, has opened new avenues in the search for habitable worlds. While thousands of exoplanets have been discovered, finding exomoons is much more challenging due to their smaller size and the difficulty in detecting their faint signals. However, the detection of potential candidates, such as a possible exomoon around the gas giant Kepler 1625b, suggests that moons could be common in the universe. Some of these exomoons might even lie in the habitable zones of their stars, where conditions could allow for liquid water and potentially life. The study of exomoons not only expands our understanding of planetary systems, but also raises the possibility that life could exist on worlds that are very different from Earth, perhaps thriving on a moon orbiting a distant gas giant. Meanwhile, the concept of dark stars, a theoretical type of star that could have formed in the early universe, offers a new perspective on the nature of dark matter. Dark stars would differ from regular stars in that they are powered not by nuclear fusion, but by the annihilation of dark matter particles in their cores. As dark matter particles collide, they could release energy, preventing the star from collapsing under its own gravity and allowing it to grow to enormous sizes. If dark stars existed, they would have been among the first luminous objects in the universe, providing a new way to study the early universe's conditions. Detecting such stars would provide a unique window into the behavior of dark matter and its role in cosmic evolution, offering insights into the mysterious substance that dominates the universe's mass. The study of fast radio bursts, FRBs, continues to intrigue scientists as these powerful but fleeting signals challenge our understanding of astrophysical phenomena. First discovered in 2007, FRBs are bursts of radio waves that last only milliseconds but release as much energy as the sun emits in a year. Their origins remain uncertain, with theories ranging from highly magnetized neutron stars known as magnetars to more exotic explanations like interactions with black holes or even signals from advanced extraterrestrial technology. While most FRBs come from unknown, distant sources, The discovery of a repeating FRB from a known galaxy suggests that some of these signals might originate from stable astrophysical processes. By studying FRBs, astronomers hope to use them as tools to map the distribution of matter in the universe, turning these cosmic enigmas into a new way to explore the large-scale structure of space. One of the most tantalizing possibilities in the study of neutron stars is the idea of quark stars, a type of compact object even denser than neutron stars, where the neutrons themselves break down into their constituent quarks. In such an environment, matter would exist in a state known as quark-gluon plasma, similar to the conditions thought to have existed just microseconds after the Big Bang. Quark stars, if they exist, would be incredibly dense and small, pushing the limits of our understanding of matter under extreme pressure. Detecting a quark star would provide a rare glimpse into the behavior of quarks, which are normally confined within protons and neutrons. It would also offer insights into the strong nuclear force, one of the fundamental forces that holds atomic nuclei together, deepening our understanding of the most basic building blocks of matter. As we explore the outer reaches of our own solar system, the discovery of Kuiper Belt objects, KBOs, has revealed a population of icy worlds that orbit far beyond Neptune. These objects, including Pluto, Eris, and the recently explored Arrokoth, are remnants from the solar system's formation, offering a glimpse into its early history. Some of these KBOs exhibit signs of geological activity, with surfaces shaped by past collisions and possibly even internal heat sources. Studying KBOs helps scientists understand how the outer regions of the solar system evolved, providing clues about the distribution of icy material and the processes that shape the planets. Missions like New Horizons, which flew by Pluto in 2015, have shown that even these distant, cold bodies can be dynamic and complex, challenging our perceptions of what makes a world interesting. In the search for extraterrestrial intelligence, SETI, the concept of astroengineering has emerged as a potential way to detect advanced civilizations. Astroengineering refers to large-scale projects that could be undertaken by technologically advanced societies, such as building Dyson spheres, structures that encircle a star to capture its energy output. Such projects would emit distinctive signatures, like infrared radiation from waste heat, that could be detectable from Earth. Other possibilities include stellar lifting, where a civilization could extract material from a star to prolong its life or create new habitats. The search for these technosignatures expands the range of methods used in the search for alien life, suggesting that even if a civilization is not actively transmitting radio signals, it might still leave detectable traces of its activities in the cosmos. Finding evidence of astroengineering would represent one of the most profound discoveries in human history, suggesting that life not only exists elsewhere in the universe, but has developed to a point where it can reshape its environment on a grand scale. As we continue to study the universe's fundamental forces, the pursuit of a theory of quantum gravity remains one of the greatest challenges in modern physics. Such a theory would unify quantum mechanics, which governs the behavior of particles on the smallest scales, with general relativity, which describes the structure of space-time and gravity. One promising approach is loop quantum gravity, which suggests that space-time itself is quantized, made up of tiny, discrete units called loops. In this view, space-time is not a smooth continuum, but has a granular structure at the Planck scale. Understanding quantum gravity would allow scientists to describe what happens at the very center of black holes and during the universe's earliest moments, where both quantum effects and gravitational effects are strong. It could reveal new insights into the fabric of reality itself, offering a deeper understanding of how the universe came to be. The universe, vast and enigmatic, continues to reveal itself in unexpected ways, challenging our assumptions and expanding our horizons. From the possibility of exotic states of matter to the tantalizing hints of life on distant moons and the mysteries of black holes, each new discovery deepens our sense of wonder. In this grand cosmic adventure, we are explorers charting a path through the unknown, guided by curiosity and the desire to understand our place in the universe. As we push further into the darkness, we find that the cosmos is not just a place of distant stars and galaxies, but a tapestry of mysteries woven into the fabric of space-time itself. It is a place where the very nature of existence is called into question, where reality bends and shifts in ways that we are only beginning to comprehend. And in this boundless journey, the questions we ask are as infinite as the universe itself, each one leading us closer to the heart of the mystery that surrounds us. As our journey through the universe deepens, we are constantly reminded that the cosmos is filled with wonders that challenge our understanding of reality itself. One of the most profound ideas that has emerged in recent years is the concept of the holographic universe. According to this theory, our three-dimensional world might be a projection from a two-dimensional boundary, much like a hologram. This concept, which stems from the study of black hole thermodynamics, suggests that all the information contained within a volume of space could be encoded on a surface that surrounds it. The holographic principle, originally proposed by physicist Gerard T. Hooft and later developed by Leonard Susskind, has found applications in string theory and quantum gravity, offering a potential way to reconcile the inconsistencies between quantum mechanics and general relativity. If the universe is indeed holographic, it would imply that our reality is fundamentally different from what we perceive, with the true nature of space, time, and matter being far more abstract and interconnected. The notion of a holographic universe also ties into theories about the information paradox and black hole complementarity. When matter falls into a black hole, it seems that the information about its quantum state is lost forever, contradicting the principles of quantum mechanics, which dictate that information must be conserved. The holographic principle suggests that this information is not lost but rather encoded on the event horizon of the black hole, in a way that it could potentially be recovered. This leads to the idea of black holes as cosmic hologram projectors, where the information that falls in is smeared across their surface. Resolving the information paradox is crucial for understanding the true nature of black holes and may offer insights into how space-time behaves at the quantum level. It suggests that reality at the edges of black holes could be more like a projected film, challenging our classical understanding of what it means to be inside or outside of an event horizon. As we explore deeper into the quantum realm, the idea of superposition and quantum entanglement continues to redefine our understanding of connectivity across space. In the quantum world, particles can exist in multiple states at once, a concept known as superposition, until they are measured. When particles become entangled, their properties become linked so that measuring one instantly affects the state of the other, no matter how far apart they are. This phenomenon, famously described by Einstein as spooky action at a distance, has been experimentally verified and is now being explored for practical applications like quantum computing and quantum teleportation. Some physicists propose that the fabric of space-time itself might be woven from networks of entangled particles, suggesting that the geometry of space could be an emergent property of these deep quantum connections. If true, it would mean that entanglement is not just a curious quantum phenomenon, but a fundamental aspect of the structure of reality itself, potentially explaining the interconnectedness of space-time and gravity. The concept of negative mass is another idea that challenges our understanding of physics. Negative mass, unlike ordinary matter, would respond in the opposite direction when pushed or pulled, creating behaviors that defy our everyday experiences. For example, if you applied a force to an object with negative mass, it would accelerate toward the force rather than away from it. While negative mass has not been observed directly, it appears in certain solutions to the equations of general relativity and in speculative theories about exotic matter. Some have proposed that negative mass could be involved in the formation of warp drives or stable wormholes, allowing for faster-than-light travel by creating regions where space-time is curved in unusual ways. Although these ideas remain far beyond our technological reach, they provide a fascinating glimpse into how the universe might permit phenomena that seem like pure science fiction. As we look at the vast expanse of the cosmos, the discovery of galactic superclusters and cosmic filaments reveals the immense scale of the universe's structure. Our own Milky Way is part of the Laniakea supercluster, a massive collection of galaxies that stretches across more than 500 million light-years. These superclusters are connected by long, thread-like structures known as cosmic filaments, which form the backbone of the cosmic web, with vast voids lying in between. The cosmic web represents the largest-scale structure in the universe, showing how galaxies are not randomly distributed but follow patterns shaped by gravity and dark matter. By studying these structures, scientists can trace how matter has clumped together over billions of years, providing insights into the role of dark matter in galaxy formation. Observations of the cosmic web allow us to see how the universe has evolved from its nearly uniform beginnings to the complex, clustered structure we observe today, revealing the grand design of cosmic architecture. The study of dark matter halos around galaxies has also transformed our understanding of how galaxies form and evolve. Dark matter halos are massive, invisible structures that envelop galaxies, providing the gravitational scaffolding needed to hold them together. Without dark matter, galaxies would not have enough mass to prevent stars in their outer regions from drifting away. Observations using gravitational lensing, where light from distant objects is bent by the gravity of a massive foreground object, have allowed scientists to map the distribution of dark matter around galaxies and galaxy clusters. These maps reveal that dark matter halos are far more massive than the visible galaxies they contain, suggesting that dark matter plays a dominant role in shaping the universe. Understanding the nature of dark matter halos helps us uncover the invisible architecture that guides the formation of galaxies, providing a more complete picture of how the universe's largest structures came to be. In our exploration of cosmic rays, we find particles that travel through space at nearly the speed of light, carrying clues about some of the most energetic processes in the universe. These high-energy particles originate from sources like supernovae, neutron stars, and active galactic nuclei, but some cosmic rays are so energetic that their origin remains unknown. When cosmic rays strike Earth's atmosphere, they create showers of secondary particles that can be detected by ground-based observatories like the Pierre Auger Observatory in Argentina. By studying these particles, scientists can learn about the conditions in distant, violent astrophysical environments, as well as the processes that accelerate particles to such extreme speeds. Cosmic rays also pose challenges for space exploration, as they represent a significant radiation hazard for astronauts on long-duration missions. Understanding their behavior and sources is crucial for both advancing our knowledge of high-energy astrophysics and protecting future space travelers. As we contemplate the future of space exploration, the concept of space habitats becomes increasingly important. While Mars has long been seen as a potential second home for humanity, some scientists and engineers are exploring the idea of creating artificial habitats in space, such as O'Neill cylinders and Bernal spheres. These massive rotating structures would simulate gravity through centrifugal force, allowing humans to live and work in space without the health risks associated with microgravity. Space habitats could be built using materials mined from asteroids or the moon, providing a sustainable source of resources. Such habitats could serve as stepping stones for deeper space exploration, allowing for the construction of space-based industries, research facilities, and even entire space-based communities. The vision of space habitats is not just about survival. It's about creating a future where humanity can thrive among the stars, using the resources of the solar system to support a new era of exploration. The study of subsurface oceans on icy moons like Europa and Enceladus has sparked excitement about the potential for life beyond Earth. These moons, with their thick ice crusts and hidden oceans, could provide environments where microbial life thrives, protected from the harsh radiation of space. Tidal forces from their parent planets, Jupiter and Saturn, create internal heating through friction, keeping these oceans in a liquid state despite the frigid temperatures at the surface. Observations of plumes of water vapor erupting from Enceladus suggest that organic molecules and other building blocks of life might be present in its subsurface ocean. Future missions, like NASA's Europa Clipper and potential landers, aim to study these plumes and the chemistry of these hidden oceans more closely, searching for signs of life. Discovering even microbial life in such environments would profoundly change our understanding of the universe, suggesting that life could be common wherever water and energy sources are found. Another profound idea in cosmology is the notion of time as a dimension that could be traversed, similar to space. In Einstein's theory of relativity, time and space are intertwined in a four-dimensional continuum known as spacetime. While we experience time as a one-way flow from past to future, general relativity allows for the theoretical possibility of closed time-like curves, paths through spacetime that loop back on themselves. These curves could, in principle, allow for time travel, though they would require conditions like rotating black holes or cosmic strings to exist. The study of time as a dimension raises philosophical questions about causality, free will, and the nature of reality, as well as the paradoxes that might arise if time travel were possible. It suggests that the universe could be far more flexible than our linear perception of time suggests, offering a glimpse into the deeper workings of space-time that govern the cosmos. As we explore these ideas, from the quantum realms to the grand cosmic scales, we are constantly reminded of how much we still have to learn about the universe. Each discovery challenges us to think beyond our current understanding, to imagine new possibilities, and to embrace the unknown. The mysteries of the cosmos are not just puzzles to be solved. They are invitations to explore, to question, and to marvel at the incredible complexity and beauty of existence. In this endless journey, the universe reveals itself as a place of boundless wonder, where the smallest particles and the largest galaxies are connected in ways we are only beginning to understand. It is a story that spans time and space, a story that we are a part of, and one that continues to unfold with each new question we dare to ask about the nature of reality. As we continue to probe the mysteries of the universe, we find ourselves confronting ideas that seem almost impossible, yet are grounded in the deepest principles of modern physics. One such idea is the concept of parallel universes, or the many-worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event has multiple possible outcomes, the universe splits into branches, with each outcome playing out in a different reality. Imagine making a choice between turning left or right. In the many-worlds interpretation, one version of you takes the left path while another takes the right, each inhabiting a separate universe. Though this concept might sound like science fiction, it arises naturally from the equations of quantum mechanics, providing a way to explain how particles can exist in a superposition of states. If true, it would mean that there are countless versions of reality, each slightly different, coexisting alongside our own. The idea of parallel universes is not just confined to the quantum realm. In cosmology, the multiverse theory suggests that our universe could be one of many, each with its own set of physical constants and laws. This idea is an extension of the concept of cosmic inflation, where rapid expansion in the early universe could have created multiple bubble-like regions of space-time, each growing into a separate universe. These other universes might have different dimensions, values for fundamental forces, or even different forms of matter. Some might be inhospitable, with conditions that would prevent stars, planets, or life from forming. Others could be eerily similar to our own, with only slight variations. The multiverse theory offers a potential explanation for why our universe seems so finely tuned for life. It could be that we live in one of the few bubbles where conditions are just right. While evidence for the multiverse remains elusive, it provides a fascinating framework for thinking about the scope of existence beyond the observable cosmos. Another mind-bending concept is the study of quantum gravity, an area that seeks to unify the theories of quantum mechanics and general relativity. One approach to this is loop quantum gravity, which suggests that space-time itself is not continuous but made up of discrete loops or quanta. In this view, space-time is composed of tiny, indivisible units, much like the pixels on a screen. As a result, space and time might not be smooth but rather granular at the smallest scales. This theory challenges our perception of a continuous universe, suggesting that if we could zoom in far enough, we would find a fabric of reality that is woven from tiny, interconnected loops. Understanding this quantized structure could help explain what happens inside black holes and during the universe's earliest moments, where both quantum effects and gravity play a crucial role. It might even reveal new insights into the nature of time itself, suggesting that time, like space, could be broken down into fundamental building blocks. As we contemplate the extreme environments in the universe, we are drawn to the mysterious world of neutron stars. These remnants of massive stars, left behind after a supernova, are so dense that a sugar cube-sized piece would weigh as much as a mountain. Within neutron stars, the pressure is so immense that protons and electrons combine to form neutrons, creating a core of nearly pure neutron matter. Some theories propose that the cores of these stars could contain even stranger states of matter, such as quark-gluon plasma or strange matter. If true, this would mean that neutron stars could be strange stars, with cores made up of quarks rather than neutrons. These quarks, normally confined within protons and neutrons, would exist freely, creating a type of matter that we cannot replicate in laboratories on Earth. Studying neutron stars, especially through phenomena like pulsars, rapidly spinning neutron stars emitting beams of radiation, helps scientists understand how matter behaves under the most extreme conditions in the universe, offering a glimpse into the fundamental forces that govern atomic nuclei. The discovery of gravitational waves has revolutionized our understanding of the cosmos, providing a new way to observe the universe. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes or neutron stars. These waves travel across space, carrying information about their origins. Unlike light, gravitational waves are not absorbed or scattered by matter, allowing them to pass through regions of space that would be opaque to electromagnetic radiation. Since their first detection in 2015, gravitational wave observatories like LIGO and Virgo have captured dozens of these signals, revealing collisions between black holes and the interior dynamics of neutron stars. These observations have opened up a new field of multi-messenger astronomy, where data from gravitational waves is combined with observations of light and particles to gain a fuller picture of cosmic events. Gravitational waves offer a unique perspective on the universe, allowing us to observe the most energetic and dramatic events in space. In the search for extraterrestrial life, scientists are increasingly focused on studying biosignatures in the atmospheres of exoplanets. A biosignature is a chemical or physical indicator that could suggest the presence of life. For example, the simultaneous presence of gases like oxygen and methane in an exoplanet's atmosphere could indicate biological activity, as these gases would otherwise react and be depleted over time. Recent advances in telescope technology, such as the James Webb Space Telescope, have made it possible to analyze the light passing through the atmospheres of distant planets, revealing their chemical composition. By looking for patterns that cannot easily be explained by geological or atmospheric processes alone, scientists hope to find evidence that life might exist elsewhere in the galaxy. The discovery of a biosignature would be one of the most significant breakthroughs in science, offering the first hints that life might be a common feature of the universe, rather than a rare anomaly. The possibility of subsurface oceans on icy moons like Europa, Enceladus, and even Titan has become a major focus in the search for life within our own solar system. These moons, with their thick ice crusts and liquid water oceans beneath, are among the most promising places to look for life beyond Earth. On Enceladus, plumes of water vapor have been detected erupting from cracks in the ice, indicating a subsurface ocean in contact with the moon's rocky core. This interaction could provide the necessary chemical energy for life, similar to hydrothermal vents found on Earth's ocean floor. Similarly, Europa is believed to have a deep ocean beneath its icy surface, potentially containing twice as much water as all of Earth's oceans combined. Future missions, such as NASA's Europa Clipper, aim to study these environments in greater detail, analyzing the composition of the plumes and searching for organic molecules that could hint at the presence of life. Discovering even microbial life in these hidden oceans would change our understanding of biology and the conditions under which life can thrive. In exploring the early universe, scientists have turned their attention to the formation of population 3 stars, the first generation of stars that formed after the Big Bang. Unlike later stars, which contain heavier elements created in the hearts of previous stars, population 3 stars were made almost entirely of hydrogen and helium, the only elements that existed in significant quantities at that time. These stars were likely much more massive than those we see today, burning brightly but living short lives before exploding in supernovae that seeded the cosmos with the first heavy elements. Finding evidence of population 3 stars would provide insights into the conditions of the universe during its first few 100 million years, revealing how the transition from a simple universe of hydrogen and helium to one rich with complex elements and galaxies occurred. Although these stars are long gone, their signatures might still be detectable in the light of the most distant galaxies, providing a window into the universe's infancy. The idea of dark energy stars presents an alternative to black holes, suggesting that what we observe as black holes might actually be objects where dark energy plays a significant role. Dark energy stars would appear similar to black holes from the outside, with a strong gravitational pull, but they would not contain a true event horizon or singularity. Instead, the dark energy within them would prevent full gravitational collapse, creating an object that mimics many of the properties of a black hole while avoiding some of the paradoxes associated with black hole physics. While this idea is speculative, it reflects the ongoing efforts to understand the nature of dark energy and how it might interact with the structure of space-time. If dark energy stars exist, they could provide a new way to think about the formation of massive objects in the universe and the role of exotic forms of energy in shaping the cosmos. One of the most intriguing and speculative ideas is the concept of the simulation hypothesis, which suggests that our entire universe might be a computer simulation run by a more advanced civilization. This idea, popularized by philosophers like Nick Bostrom, posits that if it is possible to create a simulated universe that contains conscious beings, then it might be likely that we ourselves are living in such a simulation. Proponents argue that as our own computing power increases, we might one day be able to simulate entire worlds down to the level of individual atoms, making it conceivable that a sufficiently advanced civilization could have done the same. While there is no direct evidence for the simulation hypothesis, it raises profound questions about the nature of reality, consciousness, and the possibility that our understanding of physics might be shaped by the rules of a virtual universe. It suggests that the deepest mysteries of the cosmos might not lie in the physical universe itself, but in the mind of the beings that created it. As we continue to explore these deep questions, from the possibility of parallel universes to the nature of dark energy and the search for extraterrestrial life, we are reminded that the universe is a place of endless possibilities and unanswered questions. Each new theory and discovery challenges us to expand our horizons, to think beyond the boundaries of what we know, and to imagine what might lie beyond. The mysteries of the cosmos invite us to ponder not just the physical universe, but the very nature of existence itself. It is a journey that takes us from the smallest quantum particles to the grandest structures in space, revealing a universe that is far stranger and more wondrous than we ever imagined. As we continue to explore, we remain on the edge of discovery, guided by curiosity and a sense of wonder that keeps pushing us to ask the next question, to take the next step, and to reach for the stars. As our cosmic journey extends ever deeper, we encounter ideas that test the limits of our understanding, revealing a universe far stranger than we could have imagined. One such mind-expanding concept is the idea of quantum tunneling and its implications for both the micro and macro worlds. Quantum tunneling occurs when particles pass through barriers that, according to classical physics, should be impenetrable. This phenomenon is crucial to many processes in nature, such as nuclear fusion in stars, where protons can tunnel through the repulsive forces that would normally prevent them from merging. Quantum tunneling even plays a role in modern technologies like semiconductors and tunneling microscopes, which allow us to observe atoms with unprecedented precision. On a cosmic scale, quantum tunneling may have been a key factor in the universe's early inflation, where tiny quantum fluctuations tunneled through potential energy barriers, leading to the rapid expansion that created the vast universe we see today. This ability for particles to defy classical boundaries leads us to one of the most perplexing ideas in theoretical physics: quantum immortality. Quantum immortality arises from the many worlds interpretation of quantum mechanics, suggesting that in a universe where every possible outcome of a quantum event occurs in some branch of reality, there could be versions of consciousness that survive indefinitely. For example, in a situation where a person's life is at risk due to a quantum event, in some universes they would survive while in others they would not. From the subjective perspective of that individual, they would only be aware of the branches where they continue to survive, effectively experiencing a kind of immortality. This idea is deeply speculative and highly controversial, but it offers a fascinating perspective on how quantum mechanics might interact with consciousness, challenging our perceptions of life and death, and suggesting that reality may be far more layered than we can comprehend. As we explore the universe's extreme ends, we encounter the enigmatic realm of dark fluid theory, which proposes a unified explanation for both dark matter and dark energy. Dark fluid theory suggests that what we perceive as dark matter and dark energy might be different manifestations of a single substance that behaves like dark matter in certain conditions and like dark energy in others. According to this theory, this dark fluid would have properties that change depending on the density of the universe, clumping together to form the gravitational scaffolding needed for galaxy formation, while also contributing to the accelerated expansion of space at larger scales. If dark fluid exists, it could offer a simpler explanation for the phenomena attributed to dark matter and dark energy, potentially rewriting our understanding of the universe's structure and evolution. This theory remains speculative, but it reflects the ongoing efforts by scientists to find a more cohesive picture of the universe's hidden components. The search for answers about the universe's hidden makeup leads us to the idea of axions, a hypothetical type of particle that could help explain dark matter. Axions are extremely light particles that were originally proposed to solve a problem in particle physics related to the strong nuclear force. However, they have also become a prime candidate for dark matter because they interact very weakly with ordinary matter, making them incredibly difficult to detect. If axions exist, they could form an invisible sea of particles that permeates the universe, providing the missing mass that explains the gravitational effects we observe in galaxies. Scientists have designed experiments like the Axion Dark Matter Experiment, ADMX, to search for these elusive particles, using powerful magnetic fields to convert axions into detectable signals. Discovering axions would not only solve a fundamental mystery in particle physics, but could also reveal the true nature of dark matter, helping to unravel one of the greatest puzzles in cosmology. In the realm of theoretical physics, extra dimensions have become a key concept in attempts to unify the forces of nature. String theory, for instance, requires the existence of additional spatial dimensions beyond the familiar three to be mathematically consistent. These extra dimensions could be curled up so tightly that they are imperceptible to us, existing at scales much smaller than an atom. Some models, like those involving brains, short for membranes, suggest that our universe might be a three-dimensional brain floating in a higher dimensional space. Gravity could leak into these extra dimensions, which might explain why it appears so much weaker compared to the other fundamental forces. If these extra dimensions could be detected, perhaps through experiments at the Large Hadron Collider or through subtle effects on the orbits of planets, it would revolutionize our understanding of space-time, offering a new way to think about the structure of the universe and our place within it. One of the most speculative yet fascinating ideas is that of time crystals, a new phase of matter that breaks the symmetry of time itself. Traditional crystals, like diamonds or salt, are composed of atoms arranged in repeating patterns in space. A time crystal, however, is a system where the pattern repeats not in space, but in time, allowing it to oscillate without consuming energy. This discovery, first theorized in 2012 and later realized in laboratory experiments, challenges our understanding of thermodynamics, suggesting that under certain conditions, it might be possible to create systems that remain in perpetual motion without violating the laws of energy conservation. While time crystals are unlikely to become perpetual motion machines, they could have applications in quantum computing and provide new insights into the behavior of matter at the quantum level. Time crystals show that even the concept of time, which we often take for granted, might have hidden complexities that defy classical understanding. In exploring the limits of space and time, scientists have also proposed the idea of a Big Bounce as an alternative to the Big Bang. According to this theory, our universe could be part of a cyclic process where it expands and contracts in an endless series of bounces. Instead of originating from a singularity, the universe could have undergone a previous contraction phase, reaching a point of high density before bouncing back into an expansion phase. This idea avoids the problem of a singularity with infinite density, offering a way to explain the universe's origin without invoking a state where the laws of physics break down. Recent studies of cosmic microwave background radiation and models of quantum gravity have provided tentative support for the possibility of a cyclic universe. If the Big Bounce is true, it would mean that our universe is just one phase in an eternal cycle, suggesting that time itself might have no beginning or end. The possibility of a supervoid, like the one associated with the cold spot in the cosmic microwave background, raises questions about the nature of large-scale cosmic structures. Supervoids are regions of space where the density of galaxies is far lower than average, creating vast expanses of emptiness. These voids can span hundreds of millions of light years, and their existence challenges our understanding of how the universe's large-scale structure evolved. The cold spot, a region in the CMB that is colder than expected, could be the result of light passing through a supervoid and being affected by the integrated Sachs-Wolf effect, where the expansion of space within the void alters the energy of the photons. Some theories even suggest that such anomalies might be evidence of interactions between our universe and another, offering a potential hint at the multiverse. Studying supervoids helps scientists understand the distribution of matter and energy in the universe, revealing the hidden structures that shape the cosmos. The concept of cosmic censorship is another intriguing idea in the study of black holes and space-time. Proposed by physicist Roger Penrose, the cosmic censorship hypothesis suggests that the universe hides singularities, points where gravity becomes infinite, behind event horizons, preventing them from affecting the rest of space-time. This idea implies that the naked singularities, which could theoretically exist outside of black holes, would not be observable, preserving the predictability of physical laws. However, some solutions to Einstein's equations, such as those describing rotating or charged black holes, suggest that naked singularities might be possible under certain conditions. The existence of naked singularities would challenge the idea of a well-behaved universe and raise questions about the fundamental nature of space-time. If cosmic censorship fails, it could mean that the universe is even more chaotic and unpredictable than we currently believe, potentially offering new insights into the nature of gravity and quantum mechanics. In the search for extraterrestrial life, scientists have proposed the concept of shadow biospheres, hidden microbial ecosystems that could exist alongside life as we know it, but with a completely different biochemical basis. A shadow biosphere might be composed of life forms that use alternative biochemistries, such as different amino acids, or even different solvents like methane instead of water. Such life could exist in extreme environments on Earth, or on planets and moons that are inhospitable to conventional life. If a shadow biosphere exists on Earth, it might have gone undetected because our methods are tuned to recognize life based on DNA and familiar metabolic processes. Discovering a shadow biosphere would be akin to finding an alien ecosystem on our own planet, suggesting that life could arise in many different forms, each with its own unique adaptations. This idea expands the search for life beyond the conventional criteria of habitability, encouraging us to look for life in places where we might not have expected to find it. The universe, with all its complexity and wonder, continues to defy our expectations, revealing a reality that is both more intricate and more beautiful than we could have imagined. From the possibility of parallel worlds and the mysteries of dark matter to the hidden rhythms of time crystals and the strange physics of quantum gravity, each new idea invites us to rethink the nature of existence. The cosmos is not just a place to be explored. It is a grand puzzle, a story unfolding on a scale that encompasses both the infinitesimal and the infinite. As we push the boundaries of science and philosophy, we find that the universe is a place where the known and the unknown intertwine, where every discovery leads to new questions, and where the quest for understanding is itself a journey without end. In this boundless adventure, we are explorers driven by a curiosity that reaches beyond the stars, seeking answers in the vast, star-filled darkness that surrounds us, knowing that each step forward brings us closer to the heart of the mystery that is the universe. As our exploration of the universe continues, we are confronted with ideas that stretch the boundaries of our imagination and challenge our fundamental understanding of reality. One of these is the concept of cosmic topology, which explores the shape and size of the universe on the largest scales. While we often think of the universe as being infinite and boundless, there is a possibility that it could have a specific shape or structure that wraps back on itself, much like a three-dimensional version of a two-dimensional surface, like a sphere or a torus. If the universe is closed in this way, traveling far enough in one direction might eventually bring you back to your starting point, just as sailing around the Earth would. The study of cosmic topology involves analyzing patterns in the cosmic microwave background, CMB, radiation for repeating features that might indicate a finite, closed universe. If such patterns were found, they would reveal that the universe is not infinite, but instead has a defined shape and size, offering a new perspective on the nature of space. Another fascinating concept is the Bekenstein-Hawking entropy of black holes, which suggests that the entropy of a black hole, and thus the amount of information it can contain, is proportional to the area of its event horizon rather than its volume. This idea, proposed by Jacob Bekenstein and Stephen Hawking, has profound implications for our understanding of how information is stored in the universe. It suggests that the information inside a black hole could be encoded on its surface, much like a hologram. This insight has led to the development of the holographic principle, which posits that all the information in a given volume of space could be represented by data encoded on a boundary surrounding that space. The implications of this principle extend beyond black holes, offering a potential way to describe the entire universe as a hologram. It challenges our conventional notions of space, implying that the reality we experience could be a projection from a deeper, two-dimensional structure. The nature of time itself is another area where our understanding is being redefined. In classical physics, time is viewed as a continuous flow, moving from the past through the present and into the future. However, theories of quantum time suggest that time could be quantized, composed of discrete units called chronons. Just as space might be composed of indivisible units at the Planck scale, time could also have a smallest possible unit. This idea arises from attempts to reconcile quantum mechanics with general relativity, suggesting that at the most fundamental level, time does not flow smoothly, but rather ticks in tiny increments. Understanding whether time is truly continuous or discrete could have profound implications for how we perceive change and causality, potentially altering our entire understanding of physics. It would mean that at the smallest scales, the universe might operate more like a digital clock, with events unfolding in a series of quantum jumps rather than a smooth progression. The study of exotic stars, like boson stars, offers another window into the universe's extremes. Unlike ordinary stars, which are made up of protons, neutrons, and electrons, boson stars would be composed of bosons, particles that obey different statistical rules than the fermions that make up normal matter. Boson stars are purely hypothetical and would be held together by quantum mechanical effects rather than nuclear fusion. They could form from particles like axions or other dark matter candidates, creating compact objects that mimic some properties of black holes, but without a true event horizon. If boson stars exist, they could provide clues about the nature of dark matter and offer a new type of celestial object to study. They might even serve as a potential explanation for some of the mysterious phenomena we observe, such as the behavior of certain ultra-dense compact objects that do not fit neatly into our understanding of neutron stars or black holes. As we explore the universe's earliest moments, the concept of primordial gravitational waves offers a glimpse into the conditions that existed during the first fractions of a second after the Big Bang. Unlike the gravitational waves detected from merging black holes or neutron stars, primordial gravitational waves would have been generated by the rapid inflationary expansion of the universe. These waves would carry information about the state of the universe when it was just a fraction of a second old, long before the formation of atoms, stars, or galaxies. Detecting primordial gravitational waves would provide direct evidence of cosmic inflation, offering a window into the physics that governed the universe's birth. Instruments like the BICEP, background imaging of cosmic extragalactic polarization, experiment are designed to search for the faint imprints of these waves in the polarization patterns of the cosmic microwave background. Discovering them would be akin to hearing the faint echo of the universe's creation, revealing the dynamics of space-time at its most extreme. The idea of cosmic strings ties into our understanding of the universe's birth and evolution. These one-dimensional defects in space-time might have formed during phase transitions in the early universe, similar to cracks forming in ice as water freezes. Unlike ordinary strings, cosmic strings would be incredibly thin but have immense mass, capable of warping space-time around them. If they exist, cosmic strings could create unique gravitational effects, such as bending light into characteristic patterns known as gravitational lensing or producing bursts of gravitational waves as they oscillate and interact. Finding evidence of cosmic strings would provide insights into the physics of the early universe, including the conditions that prevailed during its first moments. It would suggest that the universe's fabric has hidden structures that reflect its violent origins, offering a direct link between the fundamental forces and the cosmos we observe today. The study of quantum decoherence is crucial for understanding why the quantum world appears so different from the classical world we experience. Quantum systems can exist in superpositions of states, where particles are in multiple places or states at once. However, when a quantum system interacts with its environment, this superposition collapses into a definite state, a process known as decoherence. This is why we do not see quantum effects, like superpositions, in the macroscopic world. Interactions with the environment smooth out the strange behavior of quantum particles. Understanding decoherence not only helps us bridge the gap between quantum mechanics and everyday reality, but also has practical applications in developing quantum computers, which rely on maintaining superpositions for performing complex calculations. It also raises philosophical questions about the nature of measurement and observation, suggesting that our perception of reality might be deeply tied to the quantum processes that underlie the universe. In the search for extraterrestrial life, the concept of panspermia offers a fascinating explanation for how life might spread across the galaxy. Panspermia suggests that life could be carried from one planet to another by comets, meteoroids, or even microscopic particles drifting through space. If life emerged on one world, it could be spread to others through the impact of asteroids or the ejection of material into space by powerful events like supernovae. Some proponents of panspermia even suggest that life on Earth might have originated elsewhere in the galaxy, arriving here on a comet or meteorite billions of years ago. While direct evidence for panspermia is lacking, the discovery of organic molecules on comets and meteorites has shown that the building blocks of life are common in space. If panspermia is correct, it would mean that life could be more widespread in the universe than we realize, potentially existing wherever conditions allow these seeds of life to take root. The concept of mirror matter offers a potential explanation for some of the universe's hidden mass. Mirror matter is a hypothetical form of matter that would be similar to ordinary matter, but interact with it only through gravity. It would have its own version of the particles and forces we know, but with a mirror symmetry that makes it undetectable through standard electromagnetic interactions. If mirror matter exists, it could form stars, planets, and even entire galaxies that are invisible to us, making it a potential candidate for some forms of dark matter. The existence of mirror matter would imply that our universe has a hidden symmetry, with a shadow world that exists alongside our own, interacting with it only through gravity. Detecting such matter would require indirect methods, like studying its gravitational effects on ordinary matter, and it would open up a new dimension of understanding about the universe's structure and the nature of symmetry in physics. The possibility of Planck stars presents a novel way to think about the interior of black holes. Planck stars are hypothetical objects that form when a black hole's core reaches a critical density, and quantum effects cause it to bounce back instead of collapsing into a singularity. In this view, the collapse of matter is halted by quantum gravity, creating a state where the extreme curvature of space-time is balanced by quantum pressure. A Planck star would eventually radiate away its energy through processes like Hawking radiation, allowing the black hole to shrink and evaporate over time. Unlike traditional black holes, which are thought to end in a singularity where physics breaks down, Planck stars offer a way to preserve information and avoid the paradoxes associated with black hole evaporation. If Planck stars exist, they could change our understanding of the life cycle of black holes and provide a bridge between classical general relativity and quantum gravity. Finally, the notion of metastable universes challenges our understanding of the stability of our own cosmic environment. A metastable universe is one that is stable for a long time, but not in the most stable state possible. Some theories suggest that our universe might be like a ball sitting in a shallow valley, stable for now, but with a deeper, more stable state that it could eventually transition to. Such a transition could be triggered by quantum fluctuations, causing the universe to undergo a phase change similar to how water turns to ice. If this were to happen, it would mean the end of our universe as we know it, as the laws of physics would change and atoms, stars, and planets would cease to exist in their current forms. This idea is connected to the study of the Higgs field and the energy levels associated with the Higgs boson, which plays a role in determining the stability of the vacuum. While the timescales for such a transition are likely far beyond human existence, the concept highlights the delicate balance that defines the universe's physical laws and the precarious nature of reality. In each of these concepts, from the hidden symmetries of mirror matter to the potential of time crystals and the structure of the universe's fabric, we are reminded that the cosmos is a place where the familiar gives way to the extraordinary. The universe is a vast and intricate tapestry, where every thread is woven with mysteries that challenge our most fundamental assumptions. Our quest to understand these mysteries is not just a search for answers, but a journey into the unknown, where each discovery expands the horizons of what we thought possible. It is a journey that takes us from the edges of time to the depths of space, revealing a universe that is as strange as it is beautiful, and where every question leads to new realms of wonder and possibility. In this endless exploration, we are guided by the knowledge that the universe is more than we can see or measure. It is a place where imagination meets reality, and where the mysteries of existence invite us to dream of what lies beyond. As our exploration of the universe delves further into the mysteries of existence, we encounter ideas that push the boundaries of both science and philosophy. One of these is the concept of quantum cosmology, which seeks to understand the origin and structure of the universe using the principles of quantum mechanics. Unlike classical cosmology, which deals with large-scale structures like galaxies and the cosmic microwave background, quantum cosmology explores what happened at the very moment of the Big Bang, when the universe was smaller than an atom and quantum effects dominated. This field suggests that the universe could have emerged from a quantum fluctuation, a spontaneous event where space-time itself appeared from a state of nothingness. This idea raises profound questions about the nature of existence, suggesting that the boundary between something and nothing may not be as rigid as it appears, and that the universe might be the result of processes that transcend our everyday understanding of causality and time. The study of quantum foam, a concept proposed by physicist John Wheeler, adds to this mystery by suggesting that on the smallest scales, space-time is not smooth but rather a chaotic, ever-changing foam of tiny bubbles. This quantum foam exists at the Planck scale, where distances are measured in trillionths of a meter. In this realm, space and time fluctuate wildly, creating tiny, ephemeral wormholes and microscopic black holes that appear and disappear in a fraction of a second. These fluctuations might even give rise to the virtual particles that contribute to phenomena like Hawking radiation. Quantum foam challenges our classical understanding of space-time, suggesting that the smooth fabric of reality we observe at large scales is an illusion, with a seething, dynamic undercurrent at its foundations. Understanding quantum foam could unlock the secrets of how space-time itself emerges from the quantum realm, offering insights into the birth of the universe. One of the most intriguing implications of quantum cosmology is the concept of Euclidean space-time, where time becomes a spatial dimension when describing the early universe. This idea was popularized by Stephen Hawking and James Hartle in their no-boundary proposal, which suggests that before the Big Bang, time as we know it did not exist. Instead, the universe had a finite but unbounded structure, like the surface of a sphere. In this model, time gradually emerged as a distinct dimension as the universe expanded, allowing us to experience the linear progression of past, present, and future. This perspective challenges the notion of a singular beginning, suggesting instead that the universe did not begin in a traditional sense, but rather transitioned smoothly from a state where time was indistinguishable from space. If this model is correct, it would mean that asking what came before the Big Bang might be as meaningless as asking what lies north of the North Pole, fundamentally altering our conception of time. As we explore the fundamental nature of reality, the concept of emergent space-time offers a radical perspective on how space and time might not be fundamental aspects of the universe, but instead arise from more basic quantum processes. In this view, space-time is not a pre-existing backdrop against which events occur, but is instead woven from the interactions of quantum fields. This idea is closely related to theories like entropic gravity, which suggest that gravity might emerge from the statistical behavior of microscopic degrees of freedom, much like temperature emerges from the random motions of particles in a gas. The holographic principle is another key player in this idea, proposing that the three-dimensional space we experience could be a manifestation of information encoded on a two-dimensional surface. If space-time is emergent, it means that the very fabric of reality is not a given, but a product of deeper, underlying processes that operate beyond the reach of classical physics, opening up new possibilities for understanding the universe's structure. In the realm of astrophysical mysteries, one of the most captivating puzzles is the phenomenon of ultraluminous X-ray sources, ULXs. These objects emit X-rays with an intensity far beyond what is expected from typical stellar mass black holes. Some ULXs might be intermediate mass black holes, a missing link between stellar mass black holes and the supermassive black holes at galaxy centers, but others seem to defy this explanation. Recent discoveries suggest that some ULXs might actually be neutron stars with incredibly strong magnetic fields, known as magnetars. These magnetars can emit powerful bursts of X-rays as they accrete matter from companion stars, producing luminosities that rival those of small galaxies. Understanding ULXs could provide insights into the extremes of matter, energy, and magnetic fields, offering a glimpse into the behavior of compact objects that lie on the edge of what is physically possible. As we push the boundaries of our knowledge, the study of cosmic inflation has led to the proposal of bubble universes, where different regions of space could undergo different rates of inflation, creating separate bubbles that evolve into distinct universes. This concept is often linked to eternal inflation, where the inflationary process continues indefinitely in some regions, spawning countless new universes. Each of these bubble universes could have its own set of physical laws, constants, and structures, creating a multiverse with an almost infinite variety of possibilities. Some universes might be similar to ours, while others could be radically different, with different numbers of dimensions or forces of nature. The idea of bubble universes challenges our understanding of what constitutes reality, suggesting that the observable universe might be just one small bubble in a vast cosmic sea. It also raises philosophical questions about the nature of existence, the origin of physical laws, and whether our universe is unique or part of a larger cosmic tapestry. In the study of black holes, the idea of fuzzballs has emerged as a potential resolution to some of the paradoxes associated with black holes, particularly the information paradox. According to string theory, a fuzzball is a black hole where the event horizon is replaced by a tangle of strings and branes, creating a fuzzy surface instead of a smooth boundary. In this model, the information about everything that falls into the black hole is stored in the structure of the fuzzball, avoiding the creation of a true singularity. This suggests that rather than being a simple point where physics breaks down, a black hole could be a complex object with a detailed internal structure. Fuzzballs provide an alternative way to think about how quantum information is preserved in the presence of intense gravitational fields, offering a potential path toward resolving the mysteries of quantum gravity and the nature of singularities. As we contemplate the universe's grand structure, the idea of dark flow continues to puzzle scientists. Dark flow refers to a mysterious, large-scale motion of galaxy clusters that seems to be directed toward a specific region of the sky, a motion that cannot be explained by the known distribution of matter in the universe. This phenomenon was first detected using data from the cosmic microwave background and suggests that there might be structures or influences beyond the observable universe that are tugging on these galaxies. Some theories propose that dark flow could be evidence of a multiverse, with other universes exerting gravitational effects on our own. Alternatively, it could hint at unknown aspects of gravity or dark matter. While the existence of dark flow remains a topic of debate, its implications are profound, suggesting that our observable universe might be part of a much larger and more mysterious structure, where unseen forces shape the motion of galaxies across billions of light years. The concept of time dilation takes on new dimensions when we consider gravitational time dilation in extreme environments, such as near the event horizon of a black hole. According to Einstein's theory of general relativity, time slows down in strong gravitational fields. This means that near a black hole, time could flow so slowly that an observer far away would see events near the event horizon occurring at an incredibly slow pace. This effect is not just a theoretical curiosity. It has practical implications for understanding how matter behaves as it spirals into a black hole, as well as for interpreting the signals we receive from objects in these regions. Gravitational time dilation also occurs on smaller scales, such as between the surface of the Earth and a satellite in orbit, which must be accounted for in technologies like GPS. This phenomenon reminds us that time is not an absolute constant, but is instead intertwined with the geometry of space, revealing the profound ways in which gravity shapes our experience of reality. The idea of vacuum energy and its role in the universe's accelerated expansion continues to be a major focus of cosmological research. Vacuum energy is the energy that exists in empty space due to quantum fluctuations, and it is often associated with the cosmological constant, which represents the density of dark energy. The concept of vacuum energy suggests that even the emptiest regions of space are not truly empty, but contain a sea of virtual particles and fields that give rise to a subtle but pervasive pressure. This energy is thought to be driving the accelerated expansion of the universe, causing galaxies to move away from each other at an ever-increasing rate. However, the observed value of the cosmological constant is far smaller than what theoretical calculations predict, leading to a significant mystery known as the cosmological constant problem. Understanding vacuum energy could provide insights into the nature of dark energy, the ultimate fate of the universe, and the quantum structure of space-time itself. As we continue to explore these profound mysteries, from the nature of quantum time and the structure of black holes to the vast possibilities of the multiverse, we find that the universe is a place where the boundaries of knowledge are constantly being redrawn. Each new discovery challenges us to rethink our assumptions, to look beyond the visible and the measurable, and to imagine new dimensions of reality. The cosmos is not merely a backdrop for our existence. It is a dynamic, evolving entity filled with hidden depths and strange phenomena that invite us to explore and understand. In this endless quest for knowledge, we are driven by a curiosity that reaches beyond the stars, seeking to uncover the secrets that lie hidden in the fabric of space and time. It is a journey that transcends the limits of our senses, revealing a universe that is as intricate as it is mysterious, where every answer leads to new questions, and every question opens the door to a deeper understanding of existence.